Hello, and welcome to Sleepy Science. I'm so glad you're here. Whether your thoughts are heavy, your day has stretched too long, or you simply love falling asleep to the quiet unfolding of the universe, you've found a calm place to rest your mind. Tonight, we won't talk about stars alone, but about the strange, invisible architecture that surrounds them. The magnetic threads, the cosmic echoes, the ghostly particles, and the subtle alignments that whisper secrets across billions of light years. From the skeleton of the universe to gravitational illusions, from silent forces that guide galaxies to forgotten clues etched in the background light. This episode is a gentle journey into the unseen. Nothing too loud, nothing too fast, just you, your breath, and a stream of soft science to settle into. Before we begin, I'd love to know, where in the world are you listening from, and what time is it there? Are you wrapped in a blanket beneath a sky full of quiet stars, or tucked into a room dimly lit by the glow of evening? If these quiet explorations help you sleep, or simply help you feel, please do like the video and tap subscribe. It truly helps more sleepy minds find their way here. Now, take a slow breath. Let the noise of the day slip quietly into the past, and let's begin our slow drift into the hidden patterns that shape the cosmos. The cosmic web, the skeleton of the universe you'll never see. When you look up at the night sky, maybe you see little sparkles, stars that twinkle like tiny lights on a dark blanket. It might seem like those stars are just floating out there in empty space, spread around randomly like confetti tossed across a vast and endless void. But what if I told you that space isn't really empty at all? What if the whole universe was quietly being held together by something you've never seen? Something so big, so quiet, and so invisible that it wraps around everything you know, shaping it without ever showing its face. It's called the cosmic web, and it's the secret skeleton of the universe. A hidden structure so vast and silent that it doesn't just surround galaxies, it arranges them, connects them, and even gives them a place to belong. Imagine a spider's web stretched out in all directions, but instead of catching flies, this web catches galaxies. Yes, whole galaxies, each containing billions of stars, clouds of gas planets, and perhaps even life, are hanging on these invisible threads like ornaments on a wire or jewels sewn into fabric. But the web isn't made of string or silk. It's made of something stranger. Dark matter. Dark matter is a kind of invisible substance that doesn't shine, glow, or reflect light. We can't see it, we can't touch it, but it's there. And more importantly, it has gravity. That means it can pull things toward it, shape how objects move, and mold the very structure of the cosmos. The cosmic web stretches across the entire universe, holding galaxies together like beads on a necklace, or pearls gently resting on tensioned threads. Long, long ago, almost 14 billion years back, the universe was just beginning. It wasn't full of stars or galaxies. It wasn't cold and dark like today. It was tiny, hot, and packed with energy. And inside that glowing soup of particles and light, there were tiny little bumps, slight variations in density, like gentle ripples in a still pond. These small bumps weren't random, they were quantum ripples. Tiny shifts born from the uncertainty of the early quantum world. And then, something mind-blowing happened. The universe expanded incredibly fast in an instant called inflation, and those tiny ripples got stretched out and frozen into the structure of space itself. They became the blueprint. Over billions of years, gravity began to pull matter into those tiny dips, drawing particles toward the denser spots, like sand sliding into shallow bowls. Slowly, rivers of invisible mass began to form, filaments. And at the places where the filaments crossed, gravity gathered even more matter to build galaxy clusters. Just like that, without intention, without sound, the cosmic web began to grow. These filaments are unimaginably long, hundreds of millions of light years, and they act like highways in space. Galaxies don't just sit still, they move gently along these threads, like ants crawling across bridges. You can't see, pulled slowly by the invisible fingers of gravity. The clusters of galaxies at the intersections are like glowing cities, bright and dense, while the filaments are like winding roads that connect them all across the cosmic landscape. And in between those roads, giant voids, massive, dark deserts in the universe, where there's almost nothing at all. These empty regions stretch for light, years so vast and silent that entire galaxies could vanish into them and never be seen again. The contrast between the crowded filaments and the quiet voids gives the universe its sponge-like texture, a structure that's somehow both chaotic and organized. But how do we know all this if we can't see the web with our eyes? That's where the brilliance of science steps in. Astronomers use powerful telescopes and deep sky surveys to map the positions of galaxies across the night sky. One of the biggest projects, the Sloan Digital Sky Survey, looked at more than 1 million galaxies and noticed something strange. They weren't scattered randomly like sprinkles on a cake. They formed a pattern. When scientists connected the dots, a web-like shape appeared. It was as if the universe was revealing its hidden skeleton, one galaxy at a time. That's when the truth became clear. The universe wasn't just a random collection of matter. It was structured, patterned, and connected by something deeper. Some people say the cosmic web looks a lot like a giant brain, with galaxies acting like glowing neurons, and the dark matter filaments acting like the synapses and threads that connect them. It's a poetic thought that the universe, in some strange cosmic mirror, reflects the very structure of consciousness. The idea that your brain and the universe both follow invisible architectures makes you wonder, are we made in the image of the cosmos? Or is the cosmos shaped by something we also share within us? And guess what? You live in this web right now. Our Milky Way galaxy is part of a filament in this invisible network. It's not drifting freely through empty space. It's being tugged, subtly, steadily, toward a distant cluster of galaxies, part of a gentle gravitational migration that will take billions of years. You, me, and everything we've ever known is part of this quiet current. We're sitting on a tiny blue planet that orbits a single sun, which itself is spinning within a galaxy, which is sliding silently along a filament of the cosmic web, like a leaf on an unseen stream, following a path older than memory, older than stars. And this web is not still, it's alive in a way. Not in the sense of breathing or thinking, but in the sense that it evolves, moves, and changes. Galaxies drift, stars ignite, clusters merge, the web stretches and reshapes. Within its filaments hide the echoes of ancient sound waves, called Baryon acoustic oscillations, that once rippled through the early universe like pressure waves through air. These waves left faint, frozen patterns in how galaxies are distributed, and today they help scientists measure the age of the universe and how fast it's expanding. It's like reading wrinkles on the face of an ancient being. Every ripple, every pattern tells a story. Even though the cosmic web is made of dark matter, something we can't see, touch, or fully understand, it shapes everything we can see. It's why matter clumps into stars, why stars gather into galaxies, why galaxies form into groups and clusters. Without the web, space would be a mess of drifting particles. But with it, there is structure, rhythm, and elegance. The web gives the universe form, not like a blueprint designed by hand, but like a melody shaped by natural forces, playing out over billions of years. It's the invisible geometry behind the stars. And even though you can't see the cosmic web with your eyes, you can feel it with your imagination. Every photo of a spiral galaxy, every map of clustered galaxies, every chart of cosmic structure, they're all evidence of this hidden design. The twinkling lights in the sky are just the visible tips of a deeper architecture. It's the hidden story behind every star, every glowing arc of starlight, every curve of cosmic dust. So next time you look at the sky and think, I see everything, pause and remember, you're only seeing the glowing surfaces. The real magic is happening in the shadows, in the silence, in the invisible lattice that binds it all together. It doesn't shine, it doesn't speak, but it's real. It's ancient. And it's holding you up right now, like a net gently carrying the entire universe. You'll never see it with your eyes. You'll never hold it in your hands. But you can grasp it with your mind. And once you do, once you let that understanding settle into your thoughts, you might never look at the stars the same way again. You might start to feel the web beneath your feet. You might start to imagine that even in the quietest corners of the night sky, something enormous and unseen is quietly at work, threading everything together. Because space isn't empty, it's full of wonder. And sometimes what you can't see is the most powerful thing of all. It doesn't need to shine to shape everything you know. It only needs to be real, and it is. Baryon acoustic oscillations, fossil sound waves holding galaxies in place. Not all echoes are made of sound you can hear with your ears. Some are much bigger, much older, and they whisper through the entire universe. A long, long time ago, so long ago that there were no stars, no planets, not even any galaxies. The universe was just a hot, glowing fog made of tiny particles. Imagine a really thick soup made of light and stuff so small you can't see it, all mixed together. Everything was squished close, and nothing could travel far. Not even light. It was like trying to shine a flashlight through a cloud of steam. It just bounced around everywhere. But something amazing happened in that soup. There were little wiggles, waves moving through it, just like sound waves move through the air when someone talks or sings. These were special kinds of waves that came from tiny clumps of stuff, trying to pull things together with gravity, while light pushed back. That tug of war made the soup ripple, like throwing a stone into a big cosmic pond. Scientists call these waves Baryon acoustic oscillations. Now, these weren't sounds like music or voices. Nobody had ears, and there wasn't even air to carry sound the way we know it. But these waves were real, like pressure bumps moving across the universe. They squished and stretched matter, like breathing in and out across huge distances. Then, after about 380,000 years, the soup started to cool down. When it cooled enough, all the tiny particles stopped bouncing around so much. They finally joined together to make atoms, and light could travel freely for the first time. That moment is called recombination, and it's when the universe became transparent. Like the fog clearing after a rainstorm, the ripples froze in place. Just like when you stop stirring a bowl of pudding and it settles. But their shapes stayed. Those frozen ripples became like fingerprints stamped across the sky. Even though those waves stopped moving, their patterns were left behind, stretched across space like giant invisible rings. These rings are super huge, about 500 million light years across. That's a number so big, it's hard to imagine. But it means that galaxies, those giant collections of stars, tend to show up a little more often at that exact distance from each other. It's like the universe still remembers where those waves once were. These ripples made a kind of cosmic spacing guide, helping galaxies know where to gather. And even today, they follow those patterns like dancers, moving to the beat of music that played just once, a long time ago. But how do we even know this if we can't see or hear the waves anymore? Well, scientists are like cosmic detectives. They use big telescopes to take pictures of millions of galaxies and figure out where they are in space. When they look closely, they see that galaxies aren't spread out randomly. They're arranged in a kind of pattern. And inside that pattern, they see the same ripple distance showing up over and over again. It's like the universe left behind a ruler. And that ruler helps scientists measure how big the universe is and how fast it's growing. As the universe gets bigger, the ripple pattern stretches too. So by measuring it at different times, scientists can figure out how the universe has changed. These ripples help us understand something called dark energy, a mysterious force that's making the universe expand faster and faster, like a balloon that never stops growing. By watching how the ripples stretch, scientists can learn how this invisible energy behaves. That's why these old ripples are so important. They're not just leftovers, they're clues. They help us solve one of the biggest puzzles in science. Why is the universe expanding so quickly? And they even help with another mystery called the Hubble tension, which is when two ways of measuring how fast the universe is growing don't match. Baryon acoustic oscillations help connect the early universe to the one we see today, like a bridge that lets us walk from the past into the present. But the coolest part might be what these waves teach us about sound itself. These ripples came from places where gravity pulled stuff in, and light pushed back out, creating a back and forth motion, like a drum beating in space. That gentle thumping happened everywhere. At once, in the earliest times, then it stopped. But the shapes it made stayed behind. So the way the universe is shaped today, the way galaxies form clusters and strings and big walls of stars, comes not just from bumps and crashes, but from rhythm, from pressure, from waves that once moved through the entire cosmos. And here's something to think about. You live inside those patterns. Our galaxy, the Milky Way, sits right in the middle of one of those frozen ripples. So the Earth, the Sunday, the stars you see at night, they're all part of a structure made by a wave that moved through space almost 14 billion years ago. That means your whole life is taking place inside a beat that echoed before there were even planets. It's kind of like being a drop of water sitting on a ripple in a pond, frozen in place, but still shaped by the wave. So next time you look up at the night sky and see stars twinkling, remember that the space between them isn't empty. It's shaped by something ancient, something silent, something powerful. The stars aren't just where they are by accident. They're following a pattern, like notes in a song that only played once, but left behind a melody that still guides where everything goes. And maybe, just maybe, this idea isn't just about space. Maybe it tells us something about ourselves too. If the whole universe was shaped by invisible waves, could there be waves inside you? Could your thoughts, your feelings, even your dreams be shaped by quiet rhythms you don't hear but still follow? Maybe you are, in some way, made of echoes too, just like the stars. Maybe we all are. Because the universe doesn't forget. It remembers, not with words or pictures, but with ripples, distances, and patterns. And even when the sound stops, the shape remains. So if you ever wonder how something so big, so complicated, and so beautiful came to be, remember the waves. They're still here. They just don't make noise anymore. They leave their story in silence, and we're still listening. Tidal forces, the silent shapers of galaxies and moons. Not all power in the universe comes with a bang. Not every force shouts. Some whisper so softly across the stars that you'd almost miss them. Yet they shape entire galaxies, melt the hearts of moons and pull oceans across worlds, like invisible strings. These quiet forces don't crash or burn or roar. Instead, they stretch, they twist. They shift things gently, slowly, persistently. These are tidal forces, and while you might think of tides as something that just makes the sea go in and out, tidal forces are so much more than that. They're one of the universe's oldest, quietest, and most patient artists. Have you ever stood by the ocean and watched the waves come in, then pull back again? That rhythm, the steady rise and fall of the sea, is one way the moon speaks to Earth without ever saying a word. Because even though the moon is small compared to Earth, it has gravity, and gravity, no matter how quiet, always has a voice. The moon pulls on Earth's oceans, just enough to draw them toward it, creating bulges of water, tides, that follow the moon as Earth spins. But what's truly amazing is that this simple ocean dance is just a tiny clue to something much bigger happening everywhere. From icy moons to entire galaxies, tidal forces happen because gravity is uneven. When one object in space pulls on another, like the moon pulling on Earth, it pulls harder on the side that's closer and weaker on the side that's farther away. That difference in pull creates a kind of stretching. It's as if space is gently tugging at both ends of a ball, making it slightly longer and thinner. This might seem small, almost silly, but over time, and with enough force, that stretch can reshape worlds. Let's travel to Jupiter's moon Io, for example. At first glance, it might look quiet. Just another greyish rock floating in Jupiter's massive shadow. But inside, it's anything but calm. Io is the most volcanically active world in the solar system, with lava lakes bubbling and mountains collapsing under their own heat. And what powers all that volcanic fire? Tidal forces. As Io orbits Jupiter, it gets stretched and squished again and again. The powerful gravity of Jupiter, and even its neighboring moons, pulls on Io like someone kneading a ball of dough. That endless tug of war creates friction inside, and that friction turns into heat. The result? A moon that never rests. Its very core pulses with the silent push and pull of tides. Now, let's glide over to Enceladus, a tiny icy moon of Saturn. Unlike Io, Enceladus is cold, covered in a smooth white shell of ice. But don't be fooled by the frosty surface. Hidden beneath is a warm, salty ocean, kept liquid not by sunlight, but by tidal heating. As Saturn pulls and stretches Enceladus in its orbit, the inside of the moon gets warm enough to melt the ice. That ocean occasionally breaks through the cracks at the surface and sprays into space like a frozen geyser, shooting out into the darkness. That spray is how we discovered it. We saw the signs of tides in the sky. And then there's our moon, always showing us the same face. Have you ever noticed that? No matter when or where you look up, the moon always looks back with the same familiar expression. That's not a coincidence. It's because the Earth's gravity pulled on the moon so long and so gently that it slowed the moon's rotation. Eventually, the moon became tidally locked, spinning just once each time it orbits Earth. So we only see one side forever. And even Earth has changed. Billions of years ago, our planet spun much faster. A day was only about 6 hours long, but the moon's tidal pull slowed it down. Every second, every wave, Earth's rotation shifted. Today, our days are 24. It's drifting away, little by little. About 3.8 centimeters every year. That's slower than your fingernails grow. But over billions of years, it adds up. This is the quiet magic of tidal forces. They don't knock things over, they rearrange them gently. They don't crash, they reshape. They don't force, they influence. And their work is everywhere, even where you might not expect it. Have you heard of Roche limits? That's the invisible boundary around a planet or star where tidal forces become too strong for moons to survive. If a moon gets too close, too far inside the Roche limit, the planet's tidal pull can rip it apart. Not suddenly, not violently, but piece by piece, molecule by molecule, like an old thread unraveling. Many scientists believe that Saturn's rings were formed this way, from a moon that wandered too close and was quietly dismantled by gravity itself. No explosion, just gentle disintegration over time. But tidal forces don't stop at moons and planets. They shape entire galaxies. When two galaxies drift near each other, like the Milky Way and Andromeda, which are slowly moving toward a grand collision, their stars almost never crash head on. There's too much space between them. But their tidal forces pull on each other's edges, stretching out long ribbons of stars called tidal tails, warping spiral arms, flinging stars into new orbits, or even out into deep space. These aren't just accidents, they're tidal interactions playing out across millions of years. It's like two whirlpools slowly touching and distorting each other, not with noise, but with pull. Right now, our galaxy is stealing stars from smaller ones. Astronomers see tidal streams, trails of stars slowly being peeled away from dwarf galaxies and absorbed into the Milky Way. These streams are like scars in the sky, telling the story of past encounters. Every one of them is proof of tidal action, an invisible hand guiding the shapes and fates of entire star systems. Even distant planets outside our solar system, exoplanets, show tidal effects. Some orbit their stars so closely that one side always faces the heat, burning in eternal day, while the other side stays frozen in eternal night. These are called tidally locked planets, and they may be too extreme for life. But the same gentle forces that lock them also stabilize orbits. slow rotations, and keep internal oceans warm. Tidal forces might even help us detect moons around faraway worlds by watching tiny wobbles in the way a planet moves. What's amazing is that tidal forces don't need to be seen to be known. You can feel their fingerprints in the shape of things, in the orbits of planets, in the cracked surface of a moon, in the spiral twist of a galaxy, and even here on Earth. In every wave you watch, in every beach you walk along, in the length of every day. Tidal forces remind us that change doesn't have to be loud to be powerful. They show us that the universe isn't just made of stuff. It's made of relationships, how close things are, how big they are, how fast they move. All of these things matter. Tidal forces are like gravity's whisper, subtle, steady, and deeply connected to time itself. Once a body is locked, once an orbit is changed, once heat is created deep inside, there's no going back. Tidal forces are like the memory of motion, quietly recorded in the shapes of moons and the rhythm of stars. So the next time you hear the word tide, don't just think of oceans. Think of volcanic moons, icy geysers, shattered rings, stretched galaxies, and slowly changing planets. Think of a force that doesn't need fire or thunder to leave its mark. It just pulls, and pulls, and pulls, until everything, eventually, listens. Because in this universe, the quietest forces are sometimes the strongest. They don't shout, they shape. Magnetic fields of the cosmos, the hidden sculptors of the universe. Some of the most powerful forces in the universe are the ones you cannot see, touch, or even feel, unless you know how to look. We often think of the cosmos as governed by gravity, by mass pulling on mass, by the slow ballet of stars and galaxies locked in orbits and spirals. But there's another player, subtler, less understood, yet no less essential: magnetism. Not the kind that sticks your fridge closed or steers a compass needle, but colossal, invisible fields that thread through stars, weave across galaxies, and ripple through interstellar space like ghostly scaffolding. These are the magnetic fields of the cosmos, the hidden sculptors that guide plasma, shape solar winds, ignite flares, regulate accretion disks, and even influence the very birth and death of stars. Unlike light, they do not shine. Unlike gravity, they don't simply pull. Instead, they twist, tangle, bend, and resist, offering structure to the most chaotic regions of space. And although they are invisible to the eye, their fingerprints are everywhere. We see them in the swirling arms of spiral galaxies, in the collimated jets of quasars that stretch across millions of light years, in the delicate loops arcing over the Sunday's surface, and in the haunting polarization patterns of starlight that hint at hidden magnetic threads lying between us and the edge of the observable universe. What makes cosmic magnetism so fascinating is its dual nature, at once omnipresent and elusive. Magnetic fields cannot be seen directly, but we infer them through their influence on charged particles. In space, where plasma dominates, this influence becomes profound. Charged particles spiral along magnetic field lines. Confined, accelerated, heated, magnetic pressure can push back against gravity, regulate the collapse of gas clouds, and even determine whether a protostar ignites or dissipates. In galaxies, magnetic fields help structure the interstellar medium, shaping how gas flows, where stars form, and how radiation travels. They play a pivotal role in galactic dynamos, feedback processes, and cosmic ray propagation. And at the scale of galaxy clusters, they help support vast filaments of plasma stretching across millions of light years, anchoring matter in place like unseen wires strung across the void. Our own Sunday, modest by cosmic standards, is a magnetic monster. Its 11-year activity cycle, sunspots, solar flares, and coronal mass ejections, all are driven by complex, evolving magnetic fields. These fields twist and snap, releasing energy equivalent to billions of nuclear bombs in mere minutes. When these storms reach Earth, they ignite auroras, disrupt satellites, and even threaten electrical grids. But beyond the beauty of auroras or the threat of space weather, there's a deeper story, that we are immersed in a magnetic sea, shaped by forces that most people never realize exist. Earth's own magnetic field shields us from solar wind, deflecting charged particles and allowing life to thrive. But even this field is a mystery. It flips polarity on a timescale of hundreds of thousands of years, wobbles in strength, and originates from a liquid metal dynamo in Earth's outer core, echoing similar processes in stars and planets across the galaxy. And still, questions remain. How did cosmic magnetic fields form? Were they seeded in the Big Bang, or generated later through turbulence and motion? How do they evolve? How strong are they in the intergalactic medium? And how do they affect galaxy formation and evolution? These are not trivial puzzles. They go to the heart of astrophysics, touching everything from the early universe to the structure of the cosmic web. Magnetic fields are also key to understanding exotic objects, like magnetars, neutron stars, with magnetic fields trillions of times stronger than Earth's. These titans can twist space, fracture their crusts, and emit bursts of high-energy radiation that outshine entire galaxies for brief moments. Their fields are so intense that they distort the vacuum of space itself, a phenomenon predicted by quantum electrodynamics, but rarely observed directly. Yet they exist, silently rewriting the rules of physics in their vicinity. Even black holes, often thought of as purely gravitational phenomena, are not immune. Their accretion disks are threaded by magnetic fields that help launch relativistic jets, twin beams of plasma moving near the speed of light, powered not just by mass and spin, but by magnetism. These jets sculpt the environments of galaxies, heating interstellar gas, suppressing or triggering star formation, and regulating the growth of the galaxies themselves. In this way, magnetism becomes not just a background feature, but a cosmic governor, deciding what grows, what fades, what survives. And yet, for all this influence, magnetic fields are rarely given their due in popular science. They are too abstract, too hard to visualize, too intertwined with the messy complexity of plasma physics. But that's exactly why they matter. They remind us that not all cosmic structure comes from the obvious, that behind every glowing nebula, every rotating disk, every jet, flare, or filament, there's a field, silent but essential, holding the chaos together. Today, scientists study these fields with Faraday rotation, Zeeman splitting, synchrotron emission, and polarization measurements. Radio telescopes map magnetic influence across vast distances. Computer simulations model galactic dynamos, stellar fields, and cosmic evolution. And yet, we are still learning, still discovering that magnetism doesn't just shape matter, it shapes energy, structure, behavior. It defines what becomes possible in the universe. Perhaps the most humbling truth is this: while gravity gives the cosmos its architecture, magnetism writes the fine print. It decides how particles flow, how stars evolve, how galaxies breathe, and that fine print stretches from the core of planets to the edge of galaxy clusters, forming an invisible tapestry of forces that we are only beginning to understand. So the next time you see a spiral galaxy, a solar flare, or an aurora, know that you're not just witnessing light, you're witnessing structure, order, influence. You're seeing the quiet work of magnetic fields that have shaped the universe for billions of years without ever demanding your attention. And maybe that's the deeper lesson, that not all power is loud. Not all sculptors leave fingerprints. Some carve the cosmos in silence, and the shapes they leave behind, they are everything we see. Frame dragging, how spinning planets twist spacetime around them. What if I told you that when a planet spins, it doesn't just rotate, it drags the fabric of the universe along with it? Not metaphorically, but physically, measurably, in a way that warps reality itself. This phenomenon, called frame dragging, is one of the strangest and most profound predictions of Einstein's general relativity, and yet Most people have never heard of it, unlike the more familiar concept of gravity, which describes how mass bends space-time and causes objects to fall toward each other. Frame dragging introduces a rotational twist. It says that when a massive object like Earth spins, it pulls space-time into a gentle swirl around it, like a spoon stirring molasses. In everyday life, the effect is vanishingly small. You don't feel it walking down the street. But in the realm of physics, it's revolutionary, because it means space is not a passive stage where matter moves, but a dynamic medium that can be dragged, stretched, and twisted by the motion of the objects within it. It means that the direction you spin matters. That motion can leave a literal fingerprint on the structure of reality. And although this idea sounds almost too wild to be true, it's not just theoretical. It has been confirmed by observation. In 2004, NASA's Gravity Probe B mission launched 4 ultra-precise gyroscopes into orbit around Earth to test 2 of Einstein's key predictions: the warping of space-time due to mass and the twisting of space-time due to rotation. The results, after years of analysis, matched the predictions of general relativity with remarkable accuracy. The gyroscope's axis of spin slowly drifted, not because of instrument error, but because Earth was literally dragging the very coordinates of space around itself as it rotated. The entire Earth was acting like a massive cosmic paddle, stirring space-time. And if Earth does this, then so does every rotating mass in the universe. Planets, stars, even black holes, especially black holes. In fact, frame dragging becomes extreme near spinning black holes, where the effect creates a region around the event horizon called the ergosphere, a zone where nothing can remain still relative to distant space. In the ergosphere, space-time is being pulled so rapidly that even light is forced to move in the direction of the spin. You can still escape if you move fast enough, but you must co-rotate. It's a region where the normal rules of motion are rewritten, and it opens the door to some of the most exotic predictions in physics, like energy extraction from rotating black holes via the Penrose process. But the implications of frame dragging go beyond the black hole's edge. They stretch into the way we understand motion, force, and reality itself. Because if space can be twisted, then direction is not absolute. Rotation is not neutral. Everything in the universe that spins, and nearly everything does, alters its surrounding space-time ever so slightly, embedding its motion into the geometry of the cosmos. You might think of space as an infinite grid, but frame dragging reminds us that this grid can swirl, that it has texture, that it remembers the motion of the masses within it. Even neutron stars, compact remnants of supernova explosions, exhibit intense frame dragging due to their extreme density and rapid spin. The faster and more massive the object, the greater the distortion. Near some of the fastest spinning pulsars, the effect becomes so pronounced that it alters the timing of signals and even the path of nearby matter. These observations aren't science fiction. They're real measurements that inform how we understand gravitational waves, the orbits of satellites, and even the dynamics of galactic cores. And yet, frame dragging remains one of the quiet forces of the universe, one that doesn't announce itself with light or explosion, but with subtle shifts in orientation, tiny angular changes, persistent and undeniable. It reveals a universe where rotation is not just kinetic energy, but a sculptor of space-time. A planet is not merely turning on its axis, it's dragging the very structure of the universe around with it. A black hole is not just consuming matter, it's imprinting its spin onto the coordinates of space itself. This has profound consequences for how we model reality. GPS satellites, for example, must account for relativistic effects, including frame dragging to maintain precision. Time ticks differently depending on your altitude and motion, and the space-time you inhabit is not static. It's being reshaped in real time by the rotation of Earth. Even the future paths of particles and light are curved not only by gravity's pull, but by the underlying swirl left behind by mass in motion. And this swirl isn't just academic. It influences accretion disks, the alignment of planetary systems, and the very structure of gravitational interactions in high-energy astrophysics. But perhaps the most haunting aspect of frame dragging is its philosophical implication, that space and time are not inert, not untouched by the things they contain, but are themselves active participants in the unfolding of the cosmos. They are responsive, fluid, almost alive in the way they record and react to motion. When you consider that every rotating object leaves a twist in space-time, you begin to see the universe not as a static container, but as a living tapestry of motion, memory, and influence. Every star that spins, every planet that turns, is not only moving through the universe, it's rewriting a small part of its structure. Your own body, your breath, your thoughts may seem insignificant on this scale, but you too are part of this web of motion. You exist within space-time, and your motion, however small, resides within its fold. The earth beneath your feet is dragging space as it turns. And you, standing still, are part of that invisible current. In this way, frame dragging becomes more than physics. It becomes a reminder that nothing truly exists in isolation. That movement is always relative. That space is not a backdrop, but a participant. So the next time you look up at a spinning planet, or imagine the rotation of a distant star, remember that it's not spinning in a vacuum. It's leaving behind a twist, a swirl, a fingerprint in the fabric of reality. And the universe is still turning, still twisting, still remembering. Einstein rings, gravity's optical illusions. Sometimes the universe bends light not to hide, but to reveal. And what it shows can be stranger than illusion. Imagine staring into the night sky and seeing a perfect ring of light, like a celestial halo floating in the dark, where no such object should exist. No lens, no glass, no trick of the atmosphere. Just a background galaxy stretched into a luminous circle by the invisible gravity of a massive object in front of it. This is not science fiction or a telescope glitch. It's called an Einstein ring, one of the most mesmerizing predictions of general relativity, and one of the clearest demonstrations that gravity doesn't just pull on matter. It bends the very path of light, named after Albert Einstein, who first theorized that massive objects could curve space-time and deflect light. These rings occur when a massive galaxy or black hole aligns perfectly between us and a more distant light source. Instead of blocking the background object, the intervening mass bends the light around itself, like a stone distorting the flow of a river, curving the background image into a circle of illumination. The result is an optical illusion created, not by lenses or mirrors, but by space-time itself. And while partial versions of this effect are more common, arcs, multiple images, distorted shapes, the full ring only appears when everything aligns with uncanny precision. The observer, the lens, and the source, all in a cosmic straight line. These rings aren't just beautiful, they're powerful tools. They allow astronomers to measure the mass of the lensing object, including the hidden dark matter that doesn't emit or reflect light. In fact, gravitational lensing, of which Einstein rings are the most striking example, is one of the only direct ways we can map dark matter by observing how it bends light from galaxies billions of light years away. And it works because space-time is not flat. It is malleable, sculpted by mass and energy, like fabric indented by weight. Light, which always follows the straightest possible path through space-time, ends up curving when that fabric is warped. So in a sense, Einstein rings are not tricks at all. They're truths revealed through distortion. They show us the invisible. They amplify faint, distant galaxies, making the farthest reaches of the cosmos visible through natural magnification. Some of the most ancient galaxies we've ever observed, teeny specks from when the universe was just a few 100 million years old, were detected only because they were magnified by gravitational lensing. In this way, Einstein rings become cosmic telescopes, constructed not by engineers but by the universe itself. They are not rare, but they are rare to see fully formed. Partial lenses are scattered across the sky, like the famous cosmic horseshoe or Cheshire cat lenses, where galaxy clusters bend light into arcs and ovals. But a complete Einstein ring is a whisper of perfect geometry in a chaotic universe. It reminds us that alignment matters, that when things line up, however briefly, they can reveal more than any isolated object ever could. And it invites us to reconsider our assumptions about light, distance, and perception. Because what you see in an Einstein ring is not the thing itself, but every possible path its light could have taken, wrapped into a loop. You're not just seeing where the galaxy is, you're seeing all the ways it could appear from here. And that realization is deeply humbling. It tells you that the image you perceive is not always the one that exists, that the shape of your view depends on the curvature between, that even light, the fastest thing in the universe, can be detoured by gravity's patient hand. This has implications far beyond pretty pictures. By studying Einstein rings, scientists can measure the Hubble constant, the rate of cosmic expansion, with independent precision. They can refine estimates of galaxy mass, understand the distribution of dark matter, and even test alternative theories of gravity. In some models, the precise structure of a lens can distinguish between standard general relativity and more exotic proposals involving extra dimensions or modified gravity laws. So each ring becomes a laboratory, not in space, but of space. A test of how reality bends when mass is involved. And as telescopes become more powerful, from Hubble to James Webb to the upcoming Euclid and Roman Space Telescope missions, we're finding more rings, sharper arcs, deeper distortions, turning the sky into a canvas of curved light and invisible mass. But there's a philosophical side to this as well. Because when you look at an Einstein ring, you are witnessing a phenomenon that forces you to question the linearity of vision. You're reminded that what looks like a circle is not a circle at all, but a straight line bent into grace by unseen curvature. That behind every image is a path, a journey, a distortion. That perception is rarely pure. In a sense, we all live within gravitational lenses, curved by bias, perspective, culture, memory. We see the world not as it is, but as it bends through the framework we inhabit. And yet, just like astronomers use lensing to see deeper into the universe, we can use awareness of our distortions to see deeper into ourselves. The ring becomes a metaphor for clarity through distortion, truth magnified by the curve. And still, the physics remains staggeringly real. Einstein's equations, which seemed abstract and mathematical when first written, now predict with stunning accuracy the very shapes we photograph in the sky. And that may be the greatest magic of all, that math written in 1915 foretold optical illusions, billions of light years away, which we now capture with digital sensors and spaceborne lenses. It's a reminder that the universe, for all its wildness, follows rules, and sometimes those rules produce beauty. Not just beauty you can see, but beauty that teaches, that informs, that stretches both vision and thought. So the next time you see an image of a warped galaxy or a mysterious arc of light circling an empty space, don't dismiss it as a fluke or trick. Look closer. You may be staring at a perfect ring, one forged not by coincidence, but by the very shape of space-time itself. A ring that wouldn't exist without mass, motion, and light all conspiring to show you something you were never meant to see. And when that happens, you're not just looking at a galaxy, you're looking through gravity's eye, and what it shows you is the universe, curved into a circle of truth. Galaxy filaments, the threads that stitch the universe together. What if the universe was never truly empty, but instead woven, stitched together by colossal strands of unseen structure that stretch across billions of light years? These aren't poetic metaphors or artists' impressions, but real, observable features called galaxy filaments. The vast thread, like formations of matter that form the backbone of our universe. Picture the cosmos, not as a random sea of scattered galaxies, but as a web, an intricate, interconnected lattice, where galaxies are not isolated islands, but points along glowing, gravitational threads. These filaments are not just big, they are the largest known structures in the universe, forming networks that span hundreds of millions of light years and connect galaxy clusters like nerve fibers, linking neurons in a brain, and just like a neural network, carries information and shapes behavior. These filaments shape the formation, evolution, and distribution of everything we see in the cosmos. They guide the flow of gas, influence the path of light, and determine where galaxies are born and how they grow. But what exactly are they? And how do we know they exist? Galaxy filaments are primarily made up of dark matter, an invisible form of mass that doesn't emit or absorb light, but which makes up most of the matter in the universe. Ordinary visible galaxies are simply the luminous traces of this invisible skeleton. By mapping the positions of millions of galaxies through massive surveys, like the Sloan Digital Sky Survey, astronomers have revealed the underlying structure. Galaxies are not randomly distributed, but instead form a cosmic web clusters at the intersections, filaments between them, and vast voids in between. These patterns emerge naturally from the physics of the early universe. Tiny fluctuations in density, seeded during cosmic inflation, grew under the influence of gravity. Regions with slightly more matter pulled in more mass, forming walls and filaments, while less dense regions became voids. Over billions of years, matter flowed along these filaments, funneled by gravity, feeding the growth of galaxy clusters, like rivers, feeding oceans. And these rivers are still flowing. Galaxies move along them, drawn toward denser nodes in a slow cosmic migration that continues to this day. But beyond their immense scale and elegance, galaxy filaments are critical to our understanding of cosmic evolution. They act as highways of material, channels through which gas, dark matter, and galaxies themselves travel. They influence star formation by regulating the inflow of gas into galaxies. They dictate the orientation of galaxies. Many spiral galaxies align their spin axes along or perpendicular to the filament they inhabit. Even black hole activity in galactic centers appears to be influenced by filamentary environment. And more recently, scientists have discovered that the hot diffuse gas in these filaments, known as the warm-hot intergalactic medium, may hold a significant fraction of the universe's missing baryonic matter, the ordinary atoms that seem to have disappeared from our models. Using X-ray and ultraviolet observations, researchers are beginning to detect this elusive component, confirming that the space between galaxies is not empty, but filled with faint, glowing plasma woven through these threads. This turns the filaments into more than structural guides. They're reservoirs of matter, energy, and evolution. They're also time machines, because light from galaxies at different distances takes time to reach us. Observing the filaments across the sky allows astronomers to peer into the past, to see how these structures have grown, merged, and shifted over billions of years. Simulations like Illustris and Millennium show this beautifully. Starting from a near uniform distribution, cosmic matter condenses into filaments, walls, and nodes, assembling the visible universe like a colossal sculpture carved by gravity itself. But what makes galaxy filaments even more compelling is their similarity to biological and neural systems. The cosmic web's architecture, when analyzed mathematically, shares surprising structural patterns with the filaments in the human brain's connectome. The way information flows between neurons, the clustering of nodes, the branching of paths, all resemble the distribution of galaxies and matter in the universe. This doesn't mean the universe is a brain, or that consciousness exists at a cosmic scale. But it does force us to ask, why do such similar structures arise in systems so vastly different in scale and nature? Is there a deeper principle of organization at work? Something about efficiency, connection, or balance that transcends size and material? And if so, what might that imply about the universe's capacity for complexity, for emergence, even for purpose? These are philosophical questions, yes, but rooted in measurable, observable science. Galaxy filaments aren't guesses. They are mapped, studied, modeled, and understood. Instruments like the Dark Energy Spectroscopic Instrument, Euclid, and the Vera Rubin Observatory are dedicated to refining our picture of this cosmic scaffolding, helping us trace its shape with unprecedented precision. And as we improve our maps, we deepen our understanding, not just of where galaxies are, but why they're there. What conditions made them form? What paths led them to cluster in one node and not another? What secrets lie in the patterns we've only begun to trace? So when you look at the night sky and see a scattering of stars and galaxies, know that what you are seeing is only the brightest dots, nodes in a far larger, darker, and more intricate tapestry. You are not seeing the lines that connect them, the filaments that channel gravity, matter, energy, and time across billions of light years. But they are there, quietly shaping everything, holding galaxies in place, feeding their growth, guiding their motion. Like threads in an ancient loom, they stitch the universe together, not with thread and needle, but with force and motion. And just as a single thread in a web feels the vibration of the whole, every galaxy, every star, every planet, including ours, exists within this grand design. Not floating alone in space, but embedded in a network older than memory. So the next time you think of space as empty, remember this: the universe is not scattered, it is woven, and you are a part of its pattern. Cosmic voids, the vast nothingness that defines everything. What if the most defining structures in the universe weren't the galaxies, stars, or glowing filaments, but the vast, silent emptiness between them? Imagine an expanse so large, so hollow, that an entire galaxy cluster could vanish inside it without touching its edges. These are cosmic voids, the enormous cavernous regions of the universe where almost nothing resides. Not black holes, not nebulas, not even the faintest starlight, just silence, darkness, and space, so empty it makes our notion of vacuum seem crowded. At first glance, they seem uninteresting, just gaps between the cosmic web, the leftover places where matter didn't quite accumulate. But in reality, these voids might hold the key to understanding the very structure, evolution, and fate of the cosmos. They are not flaws in the cosmic design, they are part of the design. Without them, the universe wouldn't have texture, balance, or the breathtaking contrast that makes the luminous structures visible at all. Like the silence between musical notes, voids give meaning to the galaxies surrounding them. Their nothingness defines the something, and they're not rare. Far from it. Cosmic voids make up more than 80% of the volume of the observable universe. These immense bubbles can span tens to hundreds of millions of light years across, with only a sprinkling of galaxies floating like specks in the vastness. If the universe were a sponge, the filaments and clusters would be the thin walls, and the voids would be the great pockets of air in between. But how do such enormous, empty spaces come to exist in a universe that began in near uniform density after the Big Bang? The answer lies in gravity, and in the small fluctuations seeded in the infant universe. As matter began to clump under gravity's pull, some regions gained mass while others were drained of it. The rich got richer, the poor got emptier. Gravity fed the overdense zones, leaving underdense regions even more barren. Over billions of years, these low-density pockets expanded faster than their surroundings, becoming the yawning voids we observe today. They aren't just passively empty, they are dynamically growing. While galaxies attract matter, voids repel it. The low-density nature of voids means there is less gravitational pull to keep things in, allowing their boundaries to stretch and swell, pushing matter outward and enhancing their size. This expansion is why galaxies at the edges of voids seem to be racing away faster than average, not just because of cosmic expansion, but due to this local void-driven flow. And studying these flows allows cosmologists to better understand the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. Voids, in this sense, act like amplifiers. Their emptiness makes the effects of dark energy more pronounced and easier to measure. But that's not all. Void environments offer a unique testing ground for theories of gravity beyond general relativity. In dense regions, gravitational interactions are complex and non-linear. But in the peaceful emptiness of voids, the equations simplify. revealing subtleties in how gravity might work on the largest scales. If our theories ever break, they may break in the void first. Interestingly, galaxies that do exist inside voids, so-called void galaxies, are different too. They tend to be bluer, younger, and less massive, often isolated and undisturbed by collisions or environmental effects. In a way, they are like cosmic introverts, evolving in solitude, unshaped by the bustle of galactic cities. Studying these lonely galaxies gives insight into how galaxies grow when left alone, offering a kind of control experiment in the natural laboratory of the universe. On a more philosophical level, cosmic voids challenge our human obsession with presence. We often look for meaning in what is, in the stars, the clusters, the light. But voids teach us to look at what isn't, and realize that absence itself can be powerful, can be defining. Just as silence frames music and stillness frames motion, the void frames the cosmos. It is not a failure of formation. It is formation's counterpart, and it's oddly poetic to realize that we live on a planet inside a star system, inside a galaxy, embedded in a filament, but surrounded on all sides by almost incomprehensible emptiness. Even our Milky Way sits at the edge of a great local void. We are not at the center of a grand structure. We are near a vast, dark breath in the universe's rhythm. The more we map these voids, the more we see the negative space of the cosmos, and how its shape sculpts everything else. Tools like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Euclid mission give us increasingly detailed maps of where the universe is not, and that map is just as important as the one showing where it is. It turns out the universe is defined not just by stars and galaxies, but by their absence, by the dark, silent, near, perfect nothing that gives the luminous structures their meaning. And perhaps, in some metaphorical sense, we are too. We think of our lives in terms of events, people, accomplishments, but maybe it's also the gaps between those things. The quiet, the waiting, the empty spaces that shape us. Maybe, like the cosmos, we are made of stars, but sculpted by silence. And if so, perhaps the void isn't something to fear, but to understand. Not a hole in the universe, but its breathing space, its heartbeat between the bangs. A reminder that nothingness isn't nothing. It's just a different kind of presence, one that holds everything in balance. Gravitational lensing, when mass warps light like a lens. Under ordinary circumstances, when you look at the night sky, you assume the stars you see lie in the direction you are looking, a straight path from light to eye, a simple line between distant object and the one observing it. But space doesn't play fair with light. Mass bends it. Gravity warps the space through which it travels. And in this invisible distortion lies one of the most poetic phenomena in astrophysics. Gravitational lensing, the cosmic illusion where massive objects bend light, not by blocking it, but by curving the very stage on which it performs. It means that the universe can act like a lens, like an invisible magnifying glass floating in space, quietly bending, duplicating, and stretching light from galaxies, millions or even billions of light years away. And what makes it beautiful is not just its mechanics, which are dazzling on their own, but what it allows us to see. Gravitational lensing lets us glimpse the unreachable, witness the unseen, and measure the otherwise immeasurable. It's a gentle trick of the cosmos, a whisper from gravity saying, "Look closer, I'll show you more." It's strange to think that something as intangible as gravity can act like glass, but Einstein's theory of general relativity made a bold claim that space-time itself isn't passive. It bends, stretches, and curves in response to mass and energy. When light passes near a massive object, like a galaxy cluster or black hole, the space around that object is curved, and light, always trying to follow the straightest possible path, ends up following the curvature. To you, as an observer, the light seems to come from a different direction, or even from multiple directions at once, creating distorted, duplicated, or ring-like images of the same source. This is not a failure of nature, it's a feature. There are different kinds of gravitational lensing, depending on the configuration and strength of the gravitational field. Strong lensing produces striking visual distortions, arcs, rings, and multiple images of the same galaxy. Weak lensing is subtler. It statistically stretches and squeezes the shapes of many background galaxies, like a silent, cosmic fingerprint of the foreground mass. Then there's microlensing, where a single star or planet temporarily magnifies the light of a more distant one behind it. Each of these effects is a window, not only into the nature of the background light source, but into the mass doing the bending, including mass we can't see. In fact, gravitational lensing has become one of the most powerful tools we have for mapping dark matter. That elusive, invisible substance that doesn't emit or absorb light, but does have gravity. Since we can't observe dark matter directly, we track how it distorts the light behind it. Like shadow puppets on a curved screen, the shapes and alignments of galaxies reveal the fingerprints of the unseen. Gravitational lensing lets us literally see the presence of matter that otherwise would be invisible. In that sense, it turns emptiness into form, warping space in a way that illuminates what would otherwise remain silent. And it doesn't just show us things more clearly, it shows us things we wouldn't have seen at all. Thanks to lensing, astronomers have discovered some of the most distant galaxies ever observed, galaxies whose light would have been too faint to detect, if not for the cosmic magnification caused by intervening clusters. These ancient signals, amplified by gravity, carry whispers from a younger universe. When galaxies were just forming, stars were igniting for the first time, and the cosmic web was still stitching itself together. Without gravitational lensing, many of these faint primordial lights would be lost in the noise of space. But more than just a magnifier, gravitational lensing also acts as a kind of time machine. Because of the way it bends and delays light, we sometimes receive multiple versions of the same astronomical event, like a supernova, each one arriving at a slightly different time due to the varying lengths of the paths light has taken. We can watch the same explosion play out over and over again, from different angles of space and moments in time. In this way, lensing makes the cosmos more theatrical. A play performed not once but with repeated showings, each framed differently by gravity. There is something deeply humbling in this. We think of space as vast and indifferent, but gravitational lensing shows that it participates in what we see, that it curates, that it collaborates. Space is not a passive backdrop. It is an active medium, bending and sculpting the light that reaches us. It is both canvas and artist. It reminds you that your vision of the universe is not always what it seems, that what appears straight may be curved, what looks nearby may be distant, and what seems singular may be many. But lensing doesn't just stretch galaxies. It asks you to consider that truth can be bent, that light can take more than one path, and that the very idea of line of sight is more philosophical than it is geometric. When you see a ring of light in the sky, an Einstein ring, you are seeing something no human eye was meant to see. The perfect alignment of observer, lens, and source, forming a cosmic circle that nature didn't draw, but gravity revealed. These rings are not common, but when they happen, they are among the most beautiful structures in the universe. Not because of what they are, but because of what they represent. A pure moment of alignment in the chaos of space. In their symmetry, there is poetry. In their structure, a silent echo of Einstein's prediction made a century ago. You might wonder, why does the universe go to such trouble to hide and then reveal itself? Why not just be visible from the start? But perhaps that's the wrong question. Perhaps the bending of light is not an obstacle to understanding, but a gift, a deeper layer that lets us see more than we otherwise could. In the lensing of light, we see the lensing of reality, a reminder that every perspective is shaped by the path you take, and every vision is warped by forces you cannot always name. Gravitational lensing also forces scientists to constantly refine their models. When observations don't match expectations, when light bends more or less than predicted, it raises questions. Is there more mass than we thought? Is dark matter distributed differently? Could gravity itself behave in unexpected ways on cosmic scales? These distortions are not just pretty artifacts, they are data. Measurements of lensing effects have helped to test general relativity, to estimate the mass of galaxy clusters, and to probe the equation of state of dark energy. Each curved arc and warped ellipse is a cosmic clue, a signature written in the handwriting of space-time. And through careful analysis of these distortions, astronomers have reconstructed vast maps of the dark matter scaffolding that holds galaxies in place. Without gravitational lensing, these invisible skeletons would remain just that, invisible. But now, with each observation, the shape of the dark universe becomes clearer. Not just a poetic phrase, but a scientific truth. Gravity bends light, and in doing so, it lets us see the shape of the unseen. And perhaps that's the deeper lesson that even what bends can reveal. That distortion can be clarity, that the very warping of light, something that might seem like an obstacle, is in fact a window. In the grand cosmic dance, gravity doesn't just pull, it paints. And in those strokes of stretched galaxies and curved light, you glimpse not just the structure of space, but the intelligence of the universe itself. Maybe your own vision, shaped by past experience, pulled by unseen forces, bent by gravity of emotion, is also a kind of lens. And maybe, like the cosmos, the truth of what you see isn't always found in the direct path, but in the curves, the echoes, the slow bending around unseen centers. Maybe that's where clarity lives, not in the straight line, but in the lens. Orbital resonance, the hidden rhythm behind planetary harmony. Of all the quiet symmetries that govern the cosmos, perhaps none is more easily overlooked, and yet more fundamental than the idea that planets and moons can sing to each other, not with sound, but through the language of motion, time, and gravity, locked into unseen rhythms that preserve harmony across millions of miles. This concept, known as orbital resonance, is not just a curiosity of celestial mechanics. It's a hidden musical code embedded in the architecture of solar systems, a gravitational choreography in which worlds pulse to ratios and intervals, like dancers stepping in sync to a beat that no one hears, but everything obeys. Imagine two moons orbiting a giant planet, say Jupiter, one circling once every 2 days, another completing its orbit every 4. Each time the inner moon laps the outer, they tug on each other with gravitational nudges at the same points in their orbits. Over time, these rhythmic gravitational whispers synchronize the system, amplifying stability or sometimes triggering chaos. These simple ratios, 2:1, 3:2, 5:3, are not arbitrary. They are nature's way of saying, let there be order in the motion of the heavens. But orbital resonance isn't just a poetic metaphor. It's real, measurable, and plays a critical role in shaping the long-term dynamics of planetary systems. Take, for example, the Galilean moons of Jupiter, Io, Europa, and Ganymede, locked into a 1:2:4 resonance that forces them into a synchronized ballet. Every time Ganymede completes 1 orbit, Europa completes 2, and Io completes 4. This gravitational pacing ensures they meet at the same points in their paths, maintaining their rhythm, and interestingly, heating their interiors through tidal flexing, which could power subsurface oceans. That's right. Orbital resonance doesn't just stabilize orbits. It creates internal friction, melting ice into potential life, sustaining water. So, in this way, a simple numerical ratio can be the reason a moon might harbor life. But this hidden harmony isn't limited to moons. It exists between planets too, even ones orbiting stars light years away in our own solar system. Pluto and Neptune are in a 3:2 resonance, which is why they never collide, despite their orbital paths crossing. For every 3 orbits Pluto completes around the Sunday, Neptune completes 2. Their mutual timing ensures that whenever Pluto comes closest to the Sunday, Neptune is safely out of the way, like 2 dancers who rehearse just enough to never step on each other's toes. And yet, Pluto's orbit is highly elliptical and tilted compared to the rest of the planets. Without this resonance, Pluto's path would be chaotic, unstable. But resonance gives it a kind of gravitational shield. It is not alignment, it's rhythm, and rhythm in the vast silence of space becomes structure. What's even more astonishing is that many exoplanetary systems, worlds orbiting other stars, seem to favor resonance too. The TRAPPIST-1 system, for instance, has 7 Earth-sized planets locked in a complex chain of orbital resonances. Their spacing and motion are not random, they're whispering to one another across space, held in line by gravity's elegant timing. Astronomers believe this resonance not only helps planets stay stable over billions of years, but may even help shepherd them into the habitable zones of their stars, increasing the likelihood of life. It's as if nature knows that life requires order, and resonance is one of its tools for making it. But resonance isn't always a stabilizer. It can also be a destroyer. In Saturn's rings, for example, gaps like the Cassini division are sculpted by orbital resonances with nearby moons. The repeated tugs of a moon on ring particles at just the right interval can clear out entire swaths of material, carving paths through the icy debris. In other cases, resonance can destabilize orbits, pushing asteroids into Earth, crossing trajectories, or driving moons into slow spirals. So resonance isn't good or bad, it's influence. It's gravity's method of coordinating behavior across time. And this influence extends beyond physics. It challenges your understanding of order and chaos. Because the universe, as chaotic as it may seem, is full of repeating patterns, and orbital resonance is one of the clearest signals of that underlying structure. It suggests that timing, pure, mathematical timing, is just as important as mass or distance when it comes to shaping the cosmos. A planet that is too heavy or too light might still survive if its timing is right. A moon too close to a giant world might be shredded, unless its orbit resonates just right. It invites you to think differently about motion, not just as a path through space, but as a relationship between objects bound by timing. And that relationship can last for billions of years. What's even more striking is how these invisible patterns have helped humans discover new worlds. In the 5th century, astronomers used anomalies in Uranus's orbit to predict the existence of Neptune. The way Uranus deviated from expectations hinted at a gravitational pull from something unseen. In a sense, Neptune's existence was revealed not through light, but through rhythm, through the silent fingerprint of orbital interaction. Even today, when studying exoplanets, scientists look for signs of orbital resonance in the transit data, small clues that reveal multiple planets timing their orbits around distant stars. So orbital resonance doesn't just describe the world, it helps us discover it. It expands our senses, allowing us to hear the gravitational music of distant systems, played out in patterns of light and shadow. It reminds you that everything is connected, not through wires or waves, but through gravity and time. The cosmos is not silent, it's symphonic, and orbital resonance is one of its most elegant melodies. You begin to realize that space isn't just filled with matter, it's filled with relationships. Orbits that could collapse into chaos instead settle into harmony. Moons that might be lost to tides stay suspended, dancing on the edge of chaos. Planets that might crash into one another are spaced just so, not by accident, but by long, slow gravitational negotiations played out over epochs. And behind it all is resonance, the silent rhythm that keeps it all from falling apart. There's a strange beauty in knowing that something as abstract as a 2-to-1 ratio can hold entire worlds in place. That harmony, in the most literal sense, can be the reason a solar system survives. And perhaps that's the lesson buried in the mechanics, that timing matters. That structure can emerge from repetition. That balance doesn't always come from symmetry, but from rhythm, whether it's the orbital resonance of planets, the heartbeat of a cell, or the steady breath that keeps you alive. In a universe that seems chaotic, resonance is a quiet promise of continuity. You don't see it, but it's there, holding everything in place. Maybe even you, Heliosphere, the invisible bubble protecting our solar system. There is a vast invisible shield stretching billions of kilometers in every direction around you, a protective bubble you've likely never seen, never felt, and perhaps never even heard of. Yet without it, life on Earth might never have existed, and your world would be relentlessly bombarded by high-energy particles from deep space. This unseen barrier is called the Heliosphere, a colossal cocoon inflated by the Sunday itself, not with gas or solid matter, but with charged particles and magnetic fields, a dynamic, sprawling envelope that serves as the solar system's first and last line of defense. It's not a wall, and it's not a dome. It's more like a force field created by the Sunday's breath, the solar wind blowing outward in all directions, carving a bubble in the interstellar medium, the sparse gas and cosmic radiation that fills the space between stars. At its heart is the Sunday, continuously spewing out this solar wind, a stream of protons and electrons traveling at hundreds of kilometers per second, extending far beyond Pluto and even past the orbit of the farthest known objects in our system. But as this wind races outward, it eventually slows and crashes into the material between stars, forming a shock like waves breaking against the shore. This boundary, called the termination shock, marks the beginning of the outer heliosphere, and beyond it lies the heliosheath, a turbulent region where solar wind and interstellar gas battle in a swirling limbo. Farther still, the edge of the bubble, the heliopause, is where the solar wind finally gives up, its strength equalized by the pressure of the interstellar medium. That is the outer skin of our solar system shield, and beyond it begins true interstellar space. But this structure is not fixed. It breathes and flexes with the Sunday's activity, expanding and contracting, depending on the strength of the solar wind and the pressure from galactic forces outside. When the Sunday is active, the heliosphere puffs up. When it's quiet, the bubble shrinks, leaving the outer planets more exposed to cosmic rays. These high-energy particles from distant galaxies, neutron stars, and supernovae can be dangerous. They can erode atmospheres, mutate DNA, and disable electronics. On Earth, the atmosphere and magnetic field provide a second layer of defense. But it's the heliosphere that bears the brunt of the cosmic onslaught, stopping or deflecting the majority of this radiation before it ever reaches the inner solar system. Without the heliosphere, Earth's protective layers might not be enough. So this invisible structure isn't just interesting, it's essential. And yet, we didn't even know it existed until the latter half of the 20th century. The first hints came from studying cosmic ray levels. Scientists noticed that the intensity of galactic radiation varied with the solar cycle, implying something solar related was filtering space radiation. But the real revelation came when the Voyager spacecraft began to leave the solar system. Launched in 1977, both Voyager 1 and Voyager 2 have since traveled tens of billions of kilometers. As they moved outward, their instruments recorded a sudden drop in solar particles and a spike in galactic radiation. In 2004, Voyager 1 crossed the termination shock. In 2012, it crossed the heliopause and officially entered interstellar space. Voyager 2 followed in 2018. These milestones weren't marked by bright lights or loud alerts, but by subtle, telltale shifts in particle energy and magnetic direction, quietly confirming the limits of the Sunday's influence. Through these data, we've learned that the heliosphere is asymmetric, pushed inward on one side, possibly by an interstellar magnetic field, giving it a comet-like shape with a blunt nose and a trailing tail. We've discovered that the heliopause isn't a static line, but a fluctuating frontier impacted by the Sunday's moods and the density of interstellar gas. We've even found that the heliosheath, the turbulent region just inside the edge, is more complex than imagined, an ever-changing zone where charged particles are accelerated and shaped into strange patterns. but perhaps most fascinating, is the role the heliosphere plays in the broader galactic environment. Our solar system orbits the center of the Milky Way, taking about 225 million years to complete one loop. And during this journey, it passes through regions of varying density, temperature, and radiation. The heliosphere acts as a galactic spacesuit, shielding the planets from these environmental changes. When we pass through dense interstellar clouds, the pressure outside increases, compressing the heliosphere and allowing more cosmic rays in. Some theories even suggest that past reductions in heliospheric shielding could be linked to mass extinctions on Earth, episodes when radiation levels rose enough to disrupt climate and biology. So in a way, the heliosphere is a silent guardian of Earth's evolutionary story, an unsung moderator of cosmic influences. And yet, we still know so little about it. There is no spacecraft currently mapping its full structure. Our best data come from a few tiny probes and indirect measurements of radiation levels and magnetic fields. That's why missions like the Interstellar Mapping and Acceleration Probe, scheduled for launch in the near future, are so vital. They'll help us understand how this protective bubble forms, how it evolves, and how it interacts with the galaxy around us. Because make no mistake, the heliosphere is not a passive shell. It's an active, dynamic interface where solar physics meets galactic physics, a borderland between star and space. Constantly shifting, occasionally turbulent, always vital. Its existence challenges us to think differently about planetary safety. We often imagine that Earth's magnetic field is our main protector, and it is, on a local scale. But the heliosphere is the macro shield, the reason cosmic rays don't flood our solar system with lethal energy. It is the solar system's immune system, responding to external threats with resilience, shaped by solar output and galactic weather. And it leads us to deeper questions. What happens to planets in systems without a heliosphere? Could they ever sustain life? Or would radiation make it impossible? What if some stars have stronger winds and thus larger, safer heliospheres? Does that increase their chances of hosting life, bearing worlds? These are not just theoretical questions. They shape how we search for habitable planets, how we understand our cosmic vulnerability, and how we interpret the Sunday's role in Earth's long-term stability. The heliosphere, unseen though it may be, becomes a key factor in life's equation. And there's something quietly poetic about that. That the breath of our star, cast out across billions of kilometers, forms an invisible shell that holds danger at bay. You don't see it, you don't feel it, but it's there, surrounding you, guarding the planets, humming softly at the edges of interstellar space. It is the Sunday's final gift, its quiet extension into the unknown, a shield born of motion and magnetism, inflated by solar wind and sculpted by galactic tides, reminding us that even in the vast silence between stars, boundaries exist, and that some of them, though invisible, make all the difference. Cosmic rays, invisible bullets, shaping stars and evolution. You wouldn't know it, but right now, your body is being pierced by invisible bullets traveling at nearly the speed of light. Not metaphorical ones, not poetic illusions, but actual high-energy particles, born from the most violent places in the universe. Cosmic rays that rain down on Earth in silence, leaving no sound, no flash, only traces in the atoms they collide with, like whispers from deep space etching their story into matter itself. And yet, these invisible visitors have helped shape everything from your atmosphere to your DNA, relics of exploding stars and mysterious forces that continue to sculpt the evolution of life and the structure of galaxies, even though we still don't fully understand where all of them come from or how they gained such unimaginable energy, raising the humbling possibility that the universe is far more dynamic, far more chaotic, and far more interconnected than we tend to imagine when we look up and see only quiet stars. When cosmic rays were first discovered in the early 20th century, no one expected the sky to be dangerous. Physicists like Victor Hess ascended in balloons with electroscopes, measuring ionizing radiation at increasing altitudes, expecting it to decrease with distance from Earth, but instead it increased, revealing a shocking truth. The cosmos itself was firing particles at us, with energies millions of times greater than anything we could create in particle accelerators. And they weren't just coming from the sun, but from beyond, from supernovae, black hole jets, active galactic nuclei, and possibly even more exotic, unknown sources, like decaying dark matter or remnants of the Big Bang. These high-speed messengers, mostly protons and atomic nuclei, are born in violent astrophysical processes, where magnetic fields and shock waves accelerate them to relativistic speeds, then eject them into the interstellar and intergalactic medium, where they wander for millions of years, tangled by cosmic magnetic fields, like leaves in turbulent rivers, until they finally arrive, crashing into Earth's atmosphere and initiating vast particle showers, secondary cascades that create muons, pions, neutrinos, and other particles that sometimes reach the ground. Though we can't see them, every second dozens of these particles pass through your body, and some are so energetic that scientists have given them dramatic nicknames like, "Oh my God, particles," because they carry more energy than a fast-pitched baseball packed into a single subatomic particle, challenging our understanding of the limits of nature and raising unsettling questions about what sort of cosmic accelerators are out there, hiding in the shadows of space and time. Yet, for all their mystery, cosmic rays have also shaped the history of life on Earth. Their ionizing energy contributes to cloud formation, weather patterns, and atmospheric chemistry. And in deep time, their flux has possibly affected mutation rates and biological evolution, especially during periods when Earth's magnetic field weakened, or when the solar system drifted into regions of space with higher radiation densities, hinting that biology and astrophysics are more entangled than we once believed. Even today, astronauts in space must be shielded from cosmic rays, because their prolonged exposure increases the risk of cancer and cognitive damage. A harsh reminder that space is not a serene void, but a constant storm of radiation sculpted by the life cycle of stars. And yet, the same rays that threaten also teach, by studying their paths and origins. We map the invisible structure of magnetic fields in the galaxy, probe the violent birthplaces of stars, and even detect clues about exotic physics, like violations of symmetry, clues about dark matter, or the behavior of fundamental forces at extreme energies. Some experiments, like the Pierre Auger Observatory or the IceCube neutrino detector, are designed to track these elusive particles, using vast arrays of detectors spread across deserts or buried in Antarctic ice, looking not for light or sound, but for faint trails of subatomic change like footprints left by invisible travelers. These efforts have revealed that cosmic rays don't arrive uniformly. Their energies and arrival directions suggest patterns, anisotropies, even possible connections to nearby galactic structures. Although the tangled web of magnetic fields makes reverse engineering their path nearly impossible, adding to their allure, like messages sent from unknown senders in unknown languages. The most energetic ones seem to come from beyond our galaxy, perhaps from active galactic nuclei or gamma ray bursts, suggesting that black holes and cosmic catastrophes may be responsible for some of the most extreme events in the universe. Not just light shows, but engines of particle violence that fling matter across space. And yet, despite their violence, these particles also connect us. The atoms in your body, the heavy elements in the Earth, even the dust between stars, all carry the fingerprint of cosmic rays. From the way they alter molecules in interstellar space to the way they help form isotopes, like carbon-Fe used in radiocarbon dating, their influence is quiet, but pervasive, like invisible sculptors, brushing against the canvas of existence. Perhaps what makes them so haunting is that they are both chaotic and patterned. Their arrival random, but their impact accumulative. They are a slow erosion, a silent rewriting, a cosmic commentary that doesn't shout but insists. A reminder that you are never untouched by the universe. Not even for a moment, and as you sit there, listening or drifting off to sleep, dozens more have passed through you, some ancient, some from beyond the galaxy, some from explosions that lit up space long before humans walked the Earth. And though you didn't feel them, though they left no wound, they may have left a trace, in your atoms, in your genes, in the long, mysterious chain of events that led to you being here now, wondering how a silent rain of cosmic bullets could be both a threat and a gift. That is the paradox of cosmic rays. Invisible, unstoppable, nearly eternal in motion. They are one of the universe's most honest voices, telling us that creation and destruction are not opposites, but dance partners, that silence can shape stars, and that sometimes the most powerful forces are not the ones we can see, but the ones we can only detect by what they leave behind. So tonight, as you breathe, remember, the cosmos doesn't just shine upon you, it passes through you, constantly, endlessly, without permission or malice. And in that quiet passage, it leaves you a message that you are, and have always been. Neutrino background, the ghost particles streaming through you. You are not as alone in your body as you think. Right now, without your permission or awareness, trillions upon trillions of ghost, like particles, are flying through you every second, streaming through the Earth, through oceans, mountains, buildings, even the heart of the Sunday itself. Without slowing down, without scattering, without interacting at all, these phantom messengers carry with them the oldest story in the universe, one so ancient it predates light itself. These are neutrinos, often called ghost particles, because they are almost entirely indifferent to the matter that surrounds them. They are electrically neutral, unimaginably small, and so elusive that out of the billions that pass through your fingernail every moment, almost none ever touch anything. But their silence is deceiving, because behind that quiet is a roaring cosmological truth, the neutrino background, an invisible ocean of primordial particles that has been washing through space since the universe was less than 1 second old. Long before atoms, stars, or even the first photons had emerged, neutrinos were already moving at nearly the speed of light, born in the chaos of the Big Bang's first second. And unlike photons, which only became free to roam after the universe cooled enough to let them decouple from matter 380,000 years later, neutrinos slipped away early, like whispers escaping a firestorm. They've been flying through the cosmos ever since, forming a nearly undetectable but ubiquitous cosmic background, the cosmic neutrino background, a relic radiation field even older than the famous cosmic microwave background, and one of the last untouched witnesses of the universe's birth. But if they're everywhere, if they're flooding you constantly, why can't you see them? Why can't we feel them, measure them, harness them? Because neutrinos are almost impossibly difficult to detect. They interact only via the weak nuclear force, and even then, their cross-section for interaction is so small that they can travel through light years of lead without being stopped. To catch even a handful, we've had to build massive detectors like Super Kamiokande in Japan or IceCube in Antarctica, cavernous, deep, underground labs filled with ultra-pure materials, waiting for the rarest flicker of Cherenkov radiation produced when a neutrino, by miracle, bumps into an atomic nucleus. Even then, most of these experiments detect higher energy neutrinos from the Sunday, supernovae, or cosmic rays, not the low energy early universe neutrinos of the cosmic neutrino background. Detecting the neutrino background would require such delicate precision that the very notion borders on science fiction. Yet it remains one of the holy grails of modern cosmology, because these ghost particles could reveal information about the first second of time itself, a period we have never directly seen. Think about that. Not the first day, or minute, or even microsecond, but the very first second, the moment everything erupted into existence, when the universe was a hot soup of quarks, gluons, leptons, and possibilities. The cosmic neutrino background, is the only known thing that can carry direct evidence from that moment, unscattered, unfiltered. To detect it would be like listening to the first breath the universe ever took. And what makes neutrinos even more strange is their quantum behavior. For decades, we believed they had no mass. But experiments revealed that neutrinos can oscillate, they change flavor as they travel, flipping between electron, muon, and tau types. This oscillation is only possible if they have mass, and so they do. But the mass is so small that we still don't know exactly how much, or even whether they follow the same mass generation rules as other particles. Neutrinos may have their own unique mass mechanism, outside the standard model of particle physics, hinting at deeper, unknown laws. They might even be their own antiparticles, a property known as Majorana nature, which could explain why there's more matter than antimatter in the universe. In a strange way, these silent travelers may hold the answer to why anything exists at all. Unlike photons, which reflect and scatter and illuminate, neutrinos pass unnoticed, indifferent, and yet they are born in the most violent places: nuclear reactions in stars, exploding supernovae, the fusion at the heart of the sun. When a star collapses, it releases Phi of its energy as a burst of neutrinos, a blinding surge of ghosts that outruns even light, arriving at our detectors hours before the visual explosion. Every second, the sun emits Phi billion solar neutrinos per square centimeter onto Earth and through you. But the cosmic neutrino background is older and colder. Its neutrinos stretch to ultra-low energies by cosmic expansion. Just like the cosmic microwave background's photons were cooled to microwave frequencies, the cosmic neutrino background neutrinos today would be around Phi Kelvin, colder than the Phi Kelvin cosmic microwave background, making them incredibly difficult to detect. Yet despite their elusiveness, their existence is not in question. Their fingerprints are all over the early universe, in the formation of light elements through Big Bang nucleosynthesis, in the cosmic microwave background's slight fluctuations, in large-scale structure simulations of galaxy distributions. Without neutrinos, the universe would not look the way it does. In fact, if neutrinos had slightly more mass, galaxies might never have formed. If they had less, the universe would be filled with too much small-scale structure. They act like a cosmic smoothing agent. Their sheer speed and abundance in the early universe helped iron out wrinkles in density, making the universe more uniform and stable. They are quiet, but they shape the loudest structures. And now, they may hold the key to mysteries that go even deeper. Some theories propose sterile neutrinos, even more elusive than the three known types, that could explain dark matter. Others wonder if relic neutrinos could be detected through clever gravitational experiments, or with ultra-sensitive relic decay detection using future quantum technologies. The truth is, the more we learn about neutrinos, the more we realize how little we understand. They refuse to fit neatly into our models. They challenge the completeness of the standard model. They move through us constantly, uninvited, unbothered, and yet possibly essential to everything. They don't ask to be seen. They don't care to be noticed. But they are there, ancient, persistent, essential. So the next time you sit quietly and imagine the space around you, don't think of it as empty. Think of it as teeming with silent messengers, ghostly threads connecting you to the first second of time, to the stars, to the supernovae, to the nuclear fusion in the sun, and to the still untold chapters of the cosmos, in a universe that often hides its greatest truths behind noise. Neutrinos are the exception, a silent story written in the particles that pass right through your soul. Axion halos, a possible shadow structure around galaxies. What if every galaxy we see, majestic spirals spinning through space, luminous arms glowing with stars, is only the tip of an iceberg, with something vast, silent, and invisible coiling around it, holding it together, shaping its destiny, not with gravity alone, but with a deeper, subtler, and still hypothetical force? What if behind the luminous structures we admire lies a hidden halo of particles so strange, so ghostly, that they pass through magnetic fields without disturbance, through matter without interaction, and yet might explain some of the deepest mysteries we face in physics. These possible halos are not made of known particles, but of axions, hypothetical entities born from a problem in quantum physics, now potentially reimagined as the scaffolding of the cosmos. To understand axion halos, you first need to know that galaxies behave in a way that suggests they are wrapped in something invisible. Stars on the outskirts of galaxies rotate at speeds that cannot be explained by visible mass alone. This is one of the clearest signs that dark matter exists. Something unseen must be exerting gravitational pull. But dark matter remains elusive, with decades of experiments failing to catch it in action. While many have looked for heavy particles called WIMPs, an entirely different possibility is quietly gaining traction: axions. These are not heavy bruisers of the particle zoo. They are light, ethereal, and originally emerged, not from cosmology, but from the strong CP problem in quantum chromodynamics, a mysterious asymmetry in the laws governing quarks and gluons. The theory goes like this: certain reactions in particle physics should violate the combined symmetry of charge and parity, CPP. But they don't, at least, not in the strong nuclear force. To resolve this, theorists proposed the existence of a new symmetry, and from this elegant mathematical tweak emerged the axion. At first, it seemed like a clean solution to a niche puzzle in particle theory, but then something strange happened. Cosmologists began to realize that axions, if they exist, would also be perfect candidates for dark matter. Unlike other particles, axions wouldn't scatter or annihilate with each other. They would move sluggishly through the universe, forming a cold, diffuse background, exactly the kind of stuff that could wrap galaxies in halos and keep them spinning the way we observe. Even stranger axions wouldn't behave like classical particles at all. Because they are bosons, and possibly with incredibly low masses, they could form a coherent field across vast distances. Imagine not a sea of bouncing marbles, but a smooth, rippling ocean of quantum fields surrounding every galaxy, gently bending the fabric of space-time. Some models even suggest that axions could form Bose-Einstein condensates on cosmic scales, a state where all the particles merge into a single quantum wave, acting in perfect unison. This would mean that the dark matter halo isn't just a collection of particles, but a unified quantum entity, a kind of galactic shadow orchestra, moving to a cosmic rhythm. Axion halos, if they exist, would not be passive. They would affect the formation of galaxies, influence the motion of stars, and possibly leave subtle imprints in gravitational lensing or cosmic background radiation. They might even interact, very weakly, with photons. This opens a fascinating possibility. Under certain conditions, axions can convert into light in the presence of strong magnetic fields. That means the universe might be whispering clues to us through regions like neutron stars or black hole surroundings, where magnetic fields are intense. Projects like ADMX and MADMAX are now trying to detect these conversions in the lab, using exquisitely sensitive microwave cavities and magnets to listen for the soft hum of an axion turning into a photon. But the real prize would be indirect, finding patterns in the large-scale structure of the universe that match predictions made by axion models. Simulations suggest that axion halos would have different density profiles than WIMP-based dark matter. They would form caustics, shell-like density spikes, and possibly generate interference patterns like ripples overlapping in a pond, due to their wave-like nature. Detecting these would be difficult, but not impossible, especially with upcoming surveys like Euclid and the Vera Rubin Observatory. And, if we do find them, it will mean that galaxies are not just islands of stars floating in space, but cosmic musical notes, wrapped in halos of quantum fields playing out a silent harmony since the beginning of time. Axion halos may even help solve another mystery, the cusp. Observations show that some galaxies have smooth dark matter cores, while simulations often predict sharp cusps. Axion wave interference could naturally smooth these out, reconciling theory with observation. In this way, a particle born from quantum elegance may also bring balance to the galaxies we see. But perhaps the most humbling part is this. If Axion halos exist, then we've been surrounded by a cosmic fog for our entire history. One we cannot see, hear, or touch. But that shapes everything we know. Every spiral arm, every star's orbit, every galactic collision would be choreographed not just by gravity, but by this invisible partner. Our telescopes would be peering not into emptiness, but through translucent veils of quantum fields, ancient and all-encompassing. And just like with neutrinos, the very structure of the universe may be deeply influenced by particles that barely interact, that float through time and space like ghosts, shaping the skeleton of the cosmos without ever asking to be noticed. The beauty of Axion theory is not just in its potential to explain dark matter, but in how it connects the smallest known forces, the math of quarks and symmetry, to the largest structures in the universe. It is a bridge between quantum subtlety and cosmic grandeur. Whether axions exist is still unknown, but the mathematics is elegant. The predictions are rich, and the stakes are enormous. If future experiments find evidence of axion-photon conversion, or if we detect wave-like behaviors in galactic structures that can't be explained by traditional cold dark matter, we may come to see axion halos, not as fantasy, but as foundational. The idea that galaxies are cradled in quantum halos, not just gravity wells, but shimmering waves of probability, may redefine how we think about space itself. So next time you look at an image of a galaxy, arms outstretched like a whirlpool in space, try to imagine what you can't see. Not just the dark matter you've heard about, but a deeper layer, humming with quantum coherence, silently holding everything in place. You are not just looking at stars, you are looking at the shadow of a particle that has never been caught. A particle that might one day explain not only the structure of galaxies, but the very reason the universe holds together at all. Geodetic precession. How gravity warps the path of time itself. What if space wasn't just a backdrop, but a living stage? Not merely where the play of matter unfolds, but a flexible actor itself, responding to mass, movement, and gravity with silent but dramatic choreography that twists not only where things go, but when they get there. Imagine spinning through the cosmos on a massive gyroscope, unaware that the very space beneath you is curving and coiling in ways that subtly shift your orientation. Not because of air or friction or magnetism, but because time and space themselves are bending under the influence of gravity, and that this distortion, this silent skew, is so real it can be measured in millimeters over months, despite happening across vast emptiness. This strange phenomenon, this barely detectable cosmic drift, is known as geodetic precession. And it's not just an obscure quirk of Einstein's general relativity. It is direct proof that gravity does more than pull. It shapes the very architecture of space-time itself. At first glance, precession seems like a mundane concept. The slow wobble in the orientation of a rotating object, like how a spinning top eventually leans and spirals as it slows down. But when we take this idea to orbit, to celestial mechanics, and to the geometry of reality itself, something extraordinary happens. Geodetic precession occurs when a massive object, say, Earth, curves the space-time around it, and a smaller object, say, a satellite or gyroscope, moves through that curvature. Even though the satellite might seem to be freely floating, isolated from friction or force, its internal orientation slowly changes over time. This isn't because of any mechanical interaction. It's because the geometry it moves through is not flat. It's curved, it's warped, and as the object moves along its orbital path, the direction of its spin axis drifts, not arbitrarily, but predictably. And in precise accordance with the curved space-time it travels through. This was famously confirmed by the Gravity Probe B mission, a satellite launched by NASA in 2004, carrying ultra-precise gyroscopes that orbited Earth for over a year. The goal: to detect tiny changes in the direction of the spin axis, changes predicted by general relativity, specifically geodetic precession, and its even more subtle cousin, frame dragging. What they found was astonishing. The gyroscopes did drift, exactly as Einstein had foreseen, not due to external forces, but due to the very shape of space-time around Earth. Gravity wasn't just a force, it was geometry. But what does this mean for you, for the way we understand movement, time, and the reality we inhabit? It means that the path you travel through space affects how time unfolds for you, and vice versa. That even in a vacuum, where no forces press or push, the shape of the road beneath your feet, or beneath your spaceship, can twist your orientation, shift your timing, bend your trajectory. Imagine flying through invisible curves, guided not by what you see, but by what space itself has become. And now realize every orbit of satellites, moons, planets, dances to this unseen tune. This is not theoretical speculation. This is physics, so precise. It can be measured by atomic clocks and laser ranging, and it reaches beyond Earth. Around massive bodies like neutron stars or black holes, the curvature becomes extreme. Geodetic precession there is not just measurable, it is dominant. A pulsar orbiting a dense star will precess at such a rate that its radio beam, a lighthouse of cosmic timing, will swing in and out of view across years. These observations again confirm that space is not passive. It flows, it bends, it remembers, and your direction of spin, your orientation in time and space, must bow to that curvature. But geodetic precession doesn't stop with objects. It affects time itself. Because in general relativity, time and space are inseparable. As your trajectory bends, so does your clock. This is why GPS satellites, which orbit high above Earth where gravity is weaker and motion is faster, must constantly correct for both special and general relativistic time dilation, and for geodetic precession. If they didn't, your phone's location would drift by kilometers each day. In a very real sense, your morning coffee relies on Einstein's equations. But let's return to something deeper. Geodetic precession reminds us that even in the most still and quiet parts of space, in regions where nothing seems to happen, time and space are not truly flat. They're shaped by mass, molded by motion. They carry memory, and as you move through them, you are not just drifting, you are evolving in relation to a changing geometry. The universe, in this view, is not a static container, but a dynamic participant. Every spin you make, every orbit you trace, echoes in the shape of the field around you. The Earth doesn't simply exist in space, it deforms it. The Moon doesn't just orbit Earth, it surfs the curved slopes of its gravitational imprint. And you, whether in a car, plane, or spacecraft, are constantly being nudged, ever so gently, by the contours of the space-time you inhabit. It is as if reality itself has texture, an invisible terrain that shapes motion, direction, and time. And the deeper implication is profound. In such a universe, there are no perfectly inertial frames, no truly straight lines. Everything is path-dependent. Orientation becomes a function of context, and motion without force becomes possible, not through propulsion, but through what we once thought was fixed. The direction of spin, the axis of rotation, is in fact malleable, fluid, influenced by the mass, energy around it. This fluidity is what allows satellites to drift, clocks to tick differently, and orbits to trace more than ellipses, to trace warped loops in a higher dimensional fabric. The universe, then, is not merely expanding, it is swirling, twisting, evolving, in ways we can now detect with exquisite sensitivity. And geodetic precession is the gentle signature of that truth. It is the whisper of curved reality, revealed not in cataclysms or explosions, but in the patient turning of gyroscopes in the silence of space. It's the ultimate paradox: movement caused by stillness, rotation without torque. To let go of the idea that space is a blank slate, and instead embrace the notion that the vacuum is sculpted, the void is shaped, and the absence of matter is still filled with force. Geodetic precession is your invitation to see gravity not as a pull, but as a path, not as a force, but as form. And once you see it, you begin to understand that everything from a spinning satellite to the motion of galaxies is participating in this grand ballet, choreographed not by Newtonian pushes and pulls, but by the pliable canvas of existence itself. Cosmic shear, the subtle stretching of light across space. Imagine looking into a perfectly still lake, expecting to see a flawless reflection, only to find that the image is gently rippling, as though some unseen hand has brushed against the surface, not forcefully, but delicately enough that you begin to doubt whether the distortion is real or a trick of your eyes. Now lift that metaphor to the cosmos. Replace the lake with the fabric of the universe, and replace your reflection with the light of galaxies billions of light years away. This is the eerie beauty of cosmic shear, a phenomenon so subtle that it leaves no immediate scars, causes no violent explosions, and bends nothing visibly, yet over time reveals that the universe itself is not as smooth or symmetrical as it appears. Unlike gravitational lensing that creates dramatic arcs and Einstein rings, cosmic shear is quiet, patient, and collective, a soft warping of the shape of distant galaxies, caused not by a single massive object, but by the large-scale distribution of matter across the cosmos. To truly understand it, you must first imagine a beam of light traveling across billions of light years uninterrupted by walls or clouds, but subtly influenced by every tiny gravitational bump along the way, invisible clumps of dark matter, galaxies you can't see, and structures you don't even know exist. These are not lenses in the traditional sense, but accumulations of mass that slightly tug and stretch the light in random directions. When astronomers study thousands, even millions of galaxies, they begin to notice a pattern. Their shapes aren't random. They appear just a bit more aligned in some regions of the sky. This slight statistical skew is not a fluke of the telescope or the atmosphere. It is the fingerprint of cosmic shear, the whisper of gravity over incomprehensible distances. What makes it even more extraordinary is that this distortion cannot be seen in a single galaxy. It only emerges in the collective. One distorted image looks normal. 10,000, all leaning in the same direction, reveal the cosmic hand that bent them. In that way, cosmic shear is not just a scientific phenomenon. It's a message, encoded in faint light, about the hidden mass that surrounds us. It tells us where dark matter hides, how galaxies clump together, and even how the universe is evolving. Through cosmic shear, we're not just observing the universe. We're reading its history. But how is something so faint even detectable? The answer lies in precision. Telescopes like the Subaru Hypersuprime, CAM, and the upcoming Euclid mission are designed to capture hundreds of millions of galaxy images and measure their ellipticity, the degree to which they appear stretched. Then, through complex statistical analysis, scientists extract the signal of cosmic shear from the noise of randomness. It's like hearing a quiet melody under a chaotic crowd, and realizing that the crowd itself is swaying to a rhythm they're not aware of. That rhythm, the pattern of distorted light, maps the gravitational terrain of the cosmos. It lets us peer into the scaffolding that holds everything together, including the dark matter web that cannot be seen directly, and more than just mapping the present. Cosmic shear is a window into cosmic evolution. As light from distant galaxies travels toward us, it doesn't just carry information about its source. It carries the memory of everything it passed along the way. Every gravitational hill, every invisible valley, leaves an imprint. In this way, cosmic shear acts like a cosmic MRI, revealing the density fluctuations that have shaped the universe since its infancy. And the implications stretch further still, because cosmic shear is sensitive to both the geometry of space and the growth of structure over time. It also becomes a powerful tool for testing dark energy, the mysterious force causing the universe to expand faster and faster. By measuring how cosmic shear changes with redshift, that is, with distance and time, scientists can infer how the expansion of the universe has evolved. If the universe is stretching space more aggressively now than before, the fingerprints of cosmic shear will reflect that. In essence, cosmic shear allows us to see how space-time has been pushed and pulled over billions of years. And that's what makes it so uniquely powerful. It doesn't just show us what is. It shows us what happened, silently, gradually, universally. No single telescope photograph will ever show a clear cosmic shear event. It's not like watching a star explode or a planet transit. It's something that reveals itself only through persistence, only through patterns across immense scales, only through trust in statistics and the belief that the universe is speaking in murmurs. And this leads us to a humbling realization. The universe doesn't need to scream to be heard. Sometimes, the most profound truths are found in whispers, the subtle collective tilt of countless galaxies, all slightly nudged by the unseen. But cosmic shear also forces us to ask unsettling questions. If the universe can subtly warp the shape of galaxies without us noticing, how else might our understanding be skewed? How many other phenomena remain invisible? Not because they are rare or weak, but because they only reveal themselves in the aggregate. When we step back far enough, wait long enough, and look closely enough, cosmic shear teaches us that even emptiness isn't truly empty. Space itself carries structure, and the light that travels through it becomes a silent archivist of its twists and tensions. We begin to understand that seeing is not always believing, because what we see is already bent. We must correct for the lens of the universe, just to understand what lies beyond it. And in doing so, we gain not just a clearer picture of the cosmos, but a deeper humility about our place in it. Every photon reaching your eye, every image captured by a telescope, has been altered by its journey, not always drastically, but just enough to require interpretation. Cosmic shear is a phenomenon that makes interpretation necessary. It turns astronomy into detective work, not just observing light, but decoding the silent signals it carries. In the end, cosmic shear is a celebration of quiet persistence, of the power of faint signals over immense scales, of the hidden forces that don't shout, but still shape everything. It reminds us that the cosmos is not static, and certainly not simple. It's a woven fabric, where light stretches slightly more here, slightly less there, revealing not the chaos of a random universe, but the subtle order of a gravitational symphony. And perhaps, most profoundly, it teaches us that even the straightest path may not be straight at all, that everything we think we see has passed through countless invisible hands before it reaches us. And that understanding the truth of the universe means learning how to listen, not to the loudest voices, but to the collective murmur of distant galaxies, leaning just slightly, ever so slightly, toward the shape of an unseen truth. Inflationary ripples, imprints of the universe's first moments. From the outside, the cosmos appears quiet, vast, and immeasurably still. But what if the deeper story of existence is hidden in something so subtle, so ancient, and so impossibly faint that it took nearly 14 billion years for us to begin noticing it? Ripples not in water, not in matter, but in space-time itself, remnants of an explosion so sudden and enormous that it stretched the very structure of reality in less than a trillionth of a second. Welcome to the strange and almost mythical world of inflationary ripples. Faint imprints left behind by the universe's most violent and foundational growth spurt, a process known as cosmic inflation, that occurred so quickly and on such a small scale that the evidence it left behind is almost like a fossilized whisper etched into the very light that permeates space. And yet, these ripples hold clues not just to what happened at the birth of time, but to how everything we now know, galaxies, matter, space, and even physical laws, came into being. Because before this moment, before inflation, the universe as we think of it didn't exist, and after it, everything changed. To understand inflation is to peer behind the curtain of the Big Bang itself, to ask what was happening when time was less than 10 to the minus 35 seconds old, when the universe was smaller than a proton and expanding faster than the speed of light, driven by a mysterious vacuum energy that hasn't been fully identified, but is suspected to be the most powerful force ever to influence our cosmos. And to study inflationary ripples is to recognize that this period wasn't smooth. It was bumpy, quantum, mechanically chaotic, a boiling cauldron of fluctuations magnified to cosmic scales, and these quantum jitters, these tiny spontaneous variations in energy, were stretched across the fabric of space by the inflationary process, frozen in place as the universe expanded unimaginably fast, eventually becoming the seeds of everything from galaxies to clusters to the great cosmic web we observe today. And the fingerprints of these ripples, faint but omnipresent, are embedded in the cosmic microwave background radiation, that dim glow from the birth of the universe that still surrounds us in every direction. Not uniform, not perfect, but speckled with minute temperature differences that are the direct descendants of those original inflationary fluctuations. Differences so small, 1 part in 100,000, that it took satellites like COBE, NAPUMAP, and Planck decades of effort to measure them with precision, and what they revealed wasn't just a snapshot of a baby universe, but a confirmation that something immense and mysterious had sculpted space itself before atoms, stars, or light even existed. With the pattern of these ripples matching the predictions of inflation with eerie accuracy, confirming that the structure of today's universe, its clumps, its voids, its balance, may all trace back to randomness on a quantum scale, that inflation blew up to cosmic proportions. But what's more mysterious is that these ripples suggest something even deeper, that the universe wasn't born from nothing in a neat pop, but from a field, an inflation field, whose energy density didn't dissipate, but remained constant during expansion, leading to an exponential doubling of space itself every tiny fraction of a second, until it eventually decayed, reheating the universe, and initiating the conditions for the Big Bang, as we more commonly think of it. And here's where it gets surreal. The theory predicts that this inflation may not have been a one-time event, that while our observable patch of space stopped inflating, other regions may have continued, or are still inflating, leading to a multiverse, an endless sea of bubble universes, each with its own laws and constants, its own physics, and maybe even its own time. And the inflationary ripples in our universe could then be just the echo of one cosmic pocket among many, the only one we can see, the only one whose imprint we can trace. But if you thought that was hard to digest, consider this. Some theories suggest that gravitational waves, ripples in spacetime, could have been created during this inflationary epoch as well, and these would show up as B-mode polarization patterns in the cosmic microwave background, a specific twist in the way light is polarized that acts like a gravitational fossil of the universe's birth. And while early announcements like BICEP 2 in 2014 excited the world with the promise of detection, it turned out that dust in our own galaxy mimicked the signal, reminding us of the immense challenge in isolating whispers from the noise of existence. But the search continues, with ever more sensitive detectors and methods being built to pick up what might be the oldest physical signal ever accessible to science. And if these inflationary gravitational waves are found, it will not only confirm inflation, but also unlock new levels of understanding about quantum gravity, about how general relativity and quantum mechanics interact at the highest energies and shortest timescales, and perhaps about why our universe has the properties it does, why it's flat, homogeneous on large scales, and filled with just the right density of matter and energy to allow complex structures like stars, planets, and thinking brains to emerge. And this is the philosophical dimension of inflationary ripples. They're not just patterns in a sky map, they're cosmic answers to questions we didn't even know how to ask. They force us to confront the strange reality that randomness and structure are not opposites, that the messiness of quantum fluctuations gave birth to the majestic order of galaxies, that the universe is not tuned like a machine but unfolded like a poem written in probabilistic stanzas. And yet one that rhymes in ways we are just beginning to hear. The inflationary model, once controversial, now stands as one of the most successful frameworks in cosmology, explaining not only the uniformity and geometry of the universe, but also its subtle imperfections. The very imperfections that allowed life to eventually emerge. And though questions remain, what exactly was the inflaton? Why did inflation end? Could we ever recreate such conditions in a lab? Is inflation eternal? And if so, what lies beyond our cosmic horizon? We are left with the humbling realization that in the cold, silent void of space, a signal exists that speaks of unimaginable violence and beauty at once, of a time when the entire universe was smaller than a molecule, but held the potential for everything that ever was or ever will be, and that you, sitting here now, listening to this, are built from the amplified tremble of a quantum field, the cooled echo of an ancient instability that happened once, everywhere, and never again, a singular breath that stretched the cosmos open and scattered the seeds of destiny across the void, a ripple that became stars, atoms, oceans, and eyes that could one day look up and try to find the source. Topological defects, cracks in the fabric of the early universe, an invisible fracture running across the infant cosmos, a scar frozen in time from a split, second misstep during the universe's birth. This is what a topological defect is. Not an object, not a particle, not a galaxy or a star, but a wound, a memory of a symmetry once broken, a remnant of the universe, failing to stay perfectly smooth as it expanded and cooled. Imagine the universe as an immense, boiling sea of energy, undifferentiated and symmetric, existing in a strange high-energy state where the laws of nature were not yet fully written. Then, almost instantly, as if cooled from molten glass to a brittle crystal, this energy solidified, symmetries shattered, forces split, particles gained identity, and in that irreversible cosmic phase transition, cracks formed, just as ice crystals form patterns in freezing water, or as metallic lattices break into boundaries. These cracks are the topological defects, flaws in the structure of space left over when regions of the universe chose different paths through symmetry breaking and couldn't reconcile with their neighbors. In condensed matter physics, we see analogies in magnetic domains, liquid crystals, and superconductors. But the early universe wasn't playing on a laboratory table. It was undergoing spontaneous symmetry breaking on a cosmic scale, and the consequences were imprinted forever. There are several types of these exotic relics. Domain walls are two-dimensional surfaces where regions of space chose different vacuum states, a theoretical boundary separating pockets of the universe that never agreed. If they existed in abundance, they'd have disastrous implications, producing anisotropies in the cosmic microwave background and drastically altering the large-scale structure of the universe. Yet, fortunately, or perhaps ominously, they appear to be absent. Next are cosmic strings, ultra-thin, one-dimensional defects that could stretch across the universe, like fault lines in space-time, possessing mass and tension so extreme that if you orbited one, your clock would tick at a different rate than someone far away. These aren't the strings of string theory, but cracks that may have formed when the universe's vacuum split between different configurations. The mathematics that governs these possibilities isn't just theoretical whimsy. It emerges naturally from field theory, especially from models like the grand unified theories, where a single primordial force fractures into the familiar quartet of gravity, electromagnetism, and the two nuclear forces. The more fundamental the symmetry that broke, the more massive or energetic the defects left behind. Monopoles, another kind, are predicted to be isolated magnetic poles, either north or south. Unlike any magnet we've ever seen on Earth, their presence would violate our everyday experience of magnetic dipoles, but not the laws of quantum field theory. And yet, despite tireless searches, no monopoles have been found. Is this because they never formed, or because cosmic inflation a near instantaneous ballooning of space-time, stretched them so far apart that none remain within our observable patch. Texture defects, more complex still, represent twisted knots in field configurations, like unstable tangles of energy that might have flickered in and out of existence, without leaving much behind. And here's the astonishing twist. Some theories suggest these defects could seed the formation of galaxies. A cosmic string's immense gravitational field might tug matter into filaments and walls. A collapsed monopole might trigger inflation itself. We often think of the universe's structure as arising purely from quantum fluctuations, but topological defects offer an alternate narrative. That structure can emerge from broken symmetry, from imperfections, from error. Isn't that a poetic inversion? That the flaws in an otherwise perfect symmetry might be what made stars, galaxies, and even us. And we've barely scratched the implications. If a cosmic string passed near Earth, it could bend space-time like a gravitational lens, producing double images of stars or galaxies. In fact, some unusual astronomical observations have been interpreted as possible string signatures, but none have been confirmed. If monopoles exist and we capture one, it would revolutionize our understanding of electromagnetism, unifying it with quantum theory in a way even Maxwell didn't foresee. And if domain walls were to reappear somehow, their immense energy densities would likely doom galaxies, and perhaps existence as we know it. These defects, though born in the tiniest slivers of time, represent the deep memory of the universe. They are fossils of the moment when nothing became something, when smoothness fractured into complexity, and when perfect symmetry collapsed into the rich, uneven universe we now inhabit. To study them is to peer into the earliest instance of creation, not through myth or metaphor, but through equations, observations, and bold theoretical scaffolding. Some physicists even wonder, could dark matter be linked to stable remnants of topological defects? Could primordial black holes, born from collapsed loops of cosmic strings, explain gravitational wave events? Could the very act of symmetry breaking be repeating now in other pockets of a wider multiverse, with each crack giving rise to a new cosmic tapestry? Perhaps even inflation itself was triggered by the annihilation of one such defect, a cosmic release of tension encoded in spacetime's very weave. These aren't just academic curiosities. If proven, topological defects would open windows into physics beyond the standard model, validating or destroying grand unified theories, testing the reach of supersymmetry, and revealing what the universe was truly like at energies trillions of times higher than we can recreate in any laboratory. In a way, they are nature's unintentional messages, leftover glitches in the code, the exception that proves the rule. They don't speak in words, but in geometry, field values, and subtle distortions etched across the cosmic microwave background. They don't obey borders or clocks. They are the most ancient survivors, older than light itself, and yet, we may never detect one directly. They could have evaporated, inflated away, or collapsed into black holes long ago. But that uncertainty isn't discouraging. It's inspiring, because it reminds us that the universe is not a perfect sphere, not a clean equation, not a solved puzzle. It's flawed, textured, asymmetrical, and it is those very imperfections that may hold the key to understanding why anything exists at all. So the next time you look into the night sky and wonder what lies beyond the stars, remember this. There may be ancient fractures crisscrossing the dark, older than galaxies, invisible and silent, but still whispering the truth of how everything began. Isocurvature perturbations, when matter and light drift out of sync. Not every ripple in the early universe was a rise or fall in density. Some were stranger, quieter, and hidden not in the brightness of what was there, but in the shifting ratios between what coexisted. While most cosmological models begin with adiabatic perturbations, fluctuations where matter, radiation, and dark matter rose and fell together like synchronized waves on a single ocean, there exists another, more elusive type of fluctuation that speaks to a deeper, more discordant possibility: Isocurvature perturbations. These are not variations in total energy, but in composition, moments when the universe remained flat in terms of gravitational potential, but internally out of sync, with matter pulling one way and radiation pulling another. Unlike the adiabatic seeds that later formed galaxies, isocurvature modes represent a misalignment, regions where light and mass decoupled slightly in their evolution, drifting out of phase in a way that leaves no direct mark on the fabric of space itself, but subtly alters the patterns of the cosmic microwave background and the growth of structure. These strange perturbations aren't just theoretical artifacts. They're possible clues to unknown processes in the earliest epochs, perhaps even to the very fields and particles that shaped reality before space-time had cooled enough to form atoms. And understanding them means digging beneath the surface of the universe's first breath, to ask not just what rose or fell, but what didn't rise together. At its heart, an isocurvature perturbation is a fluctuation in what the universe is made of, rather than how much of it there is. Imagine two regions of the early universe with exactly the same total energy, but in one, there's slightly more radiation and slightly less matter, and in the other, the reverse gravity responds only to the total energy. So space remains smooth, but the underlying components are off balance. This difference is subtle. There's no gravitational imprint to immediately notice, but it matters deeply when the universe evolves, because matter and radiation influence the universe differently. Their relative proportions affect everything from how sound waves propagated through the primordial plasma to how the temperature and polarization of the CMB unfolded. Detecting such a difference is extraordinarily difficult, because the signals they leave behind are intertwined with those of adiabatic fluctuations, and because by the time we observe the CMB, most of the universe's initial noise has been smoothed out by expansion. Yet the possibility of isocurvature modes remains one of the most provocative open questions in cosmology, not because we know they exist, but because if they do, they would point to new physics beyond the simplest inflationary models we rely on. In standard single-field inflation, the idea is simple: a scalar field drives the exponential expansion of the universe, and quantum fluctuations in that field generate the uniform, adiabatic perturbations that seed structure, but introduce a second field, something that doesn't dominate energy density, but fluctuates on its own. And suddenly the situation becomes richer. This second field could decay into dark matter, baryons, or neutrinos, imprinting its own independent fluctuations on the particle content of the universe. These fluctuations wouldn't change the overall energy density, but they'd skew the balance of species, creating isocurvature modes. Various mechanisms can generate them: curvaton fields, Axion misalignment, spectator fields, or non-thermal decay of moduli fields from string theory. Each introduces fluctuations that are out of phase with the main density perturbations, and these show up as distinct signatures in the angular power spectrum of the CMB, especially in the pattern of its peaks, their spacing, and their polarization. What makes this so compelling is that if we detect even a small admixture of isocurvature modes, it would rule out many of the most elegant inflationary models and open the door to a more complex, multi-field picture of the early universe. But we haven't seen them yet, at least not definitively. Measurements from the WMAP and Planck satellites have constrained the fraction of isocurvature perturbations to be small, less than a few % of the total. Yet, small is not none. The current limits leave room for subdominant isocurvature contributions, especially if they are correlated or anti-correlated with adiabatic modes. In these cases, the interplay between the two types of perturbations can shift the acoustic peaks in the CMB, changing their height or phase. For instance, a cold dark matter isocurvature mode that is anti-correlated with adiabatic fluctuations could cancel out some of the temperature fluctuations in specific multipole ranges, subtly altering the observed spectrum. Extracting this signal requires precise modeling and cross-correlation with large-scale structure surveys, Baryon acoustic oscillations, and CMB polarization data. It's not just about measuring power, it's about decoding interference, like analyzing a musical chord not for its volume, but for its harmonic balance. The stakes are high because isocurvature modes don't just tell us about the early universe. They tell us what kinds of matter were even possible back then. A detected isocurvature component might indicate that dark matter existed well before baryogenesis, or that its origin is tied to processes unrelated to radiation thermalization. It could also suggest that dark matter interacts in ways we haven't yet probed, perhaps via coupling to unknown scalar fields or exotic sectors that left no electromagnetic trace. Even more radically, isocurvature signatures might hint at modifications to gravity or alternative cosmologies where the initial conditions differ fundamentally from the standard inflationary narrative. These aren't just details, they are foundational shifts. The presence of even a modest isocurvature component would shake the current consensus and force theorists to expand their frameworks, perhaps reviving or refining models that were previously dismissed. One of the most fascinating aspects of isocurvature perturbations is that they embody a kind of cosmic tension, regions where the universe's contents were uncoordinated, moving toward different thermal and structural destinies. Over time, many of these differences would have smoothed out as radiation diluted and matter came to dominate. But some traces may still linger in the delicate statistics of the sky. It's a reminder that the early universe wasn't a unified orchestra, but a complex ensemble, with different sections playing slightly out of tune before harmonizing into the cosmic structure we now observe. This discord might not be visible in the brightness of galaxies or the clustering of stars, but it could be encoded in polarization maps, in statistical anomalies, or in the non-Gaussianity of the CMB. In a universe that has largely settled into order, isocurvature is the leftover dissonance, the echo of competing beginnings. To explore these possibilities, future missions will need to go beyond Planck, pushing the limits of sensitivity, angular resolution, and foreground removal. Experiments like CMBS-4, Lightbird, and the Simons Observatory are already poised to sharpen our view of the CMB's polarization, where isocurvature signals are less contaminated by late-time effects. Meanwhile, deep galaxy surveys and 21-centimeter cosmology may offer independent probes of initial conditions, giving us new ways to detect species, specific fluctuations that emerge during the first few million years. Together, these tools could enable a new kind of cosmological archaeology, not just mapping where matter went, but how different kinds of matter disagreed about where to go in the first place. What makes isocurvature perturbations so philosophically provocative is that they challenge the assumption that the universe was always in agreement with itself. They suggest a primordial phase, where the universe's ingredients were not in sync. Not because of chaos, but because of hidden rules, unknown particles, or deeper symmetries yet to be revealed. They raise questions about entropy, initial conditions, and the true nature of randomness in the cosmos. Were these fluctuations seeded by fields that no longer exist? Are they relics of higher dimensional dynamics? Are they telling us that what we call the early universe was itself the product of conflicting influences, braided together into the relatively smooth reality we now see? These are not just scientific questions. They are questions about origin, about truth beneath, apparent unity, about the possibility that even at its most primitive, the universe contained contradiction. So if someday we confirm the existence of isocurvature perturbations, not as a dominant force, but as a whisper beneath the noise, it will not just be a scientific refinement, it will be a revelation, a message that the universe, in its first moments, was not only rich in energy, but rich in complexity, that even in the absence of gravity's pull, there were disagreements, imbalances, and asymmetries that foreshadowed the diversity we now witness in stars, galaxies, and thought. And from those early disagreements came all the structured beauty that followed, not because everything moved together, but because at first they didn't. The Sachs-Wolfe effect. How gravity leaves an echo on the CMB. Imagine listening to the oldest sound in the universe. Not a song, not a word, but a subtle hiss stretching across the entire sky, whispering stories from nearly 14 billion years ago. This sound isn't carried by air or voice, but imprinted in the temperature of light itself, encoded in the cosmic microwave background, or CMB. It's the afterglow of the Big Bang, a frozen remnant of the early universe, like the echo of a fire that's long been extinguished. But within this seemingly uniform radiation lies something extraordinary. Faint temperature fluctuations, tiny wrinkles in the fabric of space that hold the clues to everything we see today. Galaxies, stars, planets, all of them trace their roots to these minute irregularities. And among them, there is a quieter, deeper mystery, a ghostly fingerprint left, not by matter, not by light, but by gravity itself. This is the Sachs-Wolfe effect, a subtle distortion in the CMB that reveals how gravity bends, stretches, and even slows down light as it journeys through the warped geometry of the universe. It's not about what emitted the light, but how space and time distorted it along the way. It's the story of how gravity, though silent, carved its voice into the cold relic of creation, and how that voice still hums in the microwave static that envelops us. To understand the Sachs-Wolfe effect, you need to step into a universe that was once blindingly hot, dense, and simple, a soup of photons, electrons, and baryons, all tangled together in a tightly coupled dance. In those first few 100,000 years, light could not travel freely. It scattered constantly off charged particles like a flashlight in thick fog. But around 380,000 years after the Big Bang, the universe cooled just enough for atoms to form, allowing photons to break free and travel vast distances unimpeded. This moment, called recombination, produced the cosmic microwave background, a snapshot of the infant cosmos. The light we see today as the CMB has been traveling ever since, stretched by the expansion of the universe from blistering ultraviolet down to gentle microwaves. But that journey was not smooth. It passed through valleys and hills of gravitational potential, places where mass clumped together or thinned out. And this is where gravity, though invisible, etched its influence onto the CMB in a measurable way. When photons climb out of a gravitational well, a dense region of space, they lose energy. Their wavelength stretches, their frequency drops, and they appear cooler to us. Conversely, when they fall into a gravitational well, they gain energy and appear warmer. But this isn't as simple as rolling a ball up and down a hill. Space itself is expanding, and with it, gravitational potentials change. If a photon leaves a gravitational well, that gets shallower over time due to cosmic expansion. It doesn't lose as much energy as it gained falling in. This imbalance, caused by the evolution of gravitational potential, is the integrated Sachs-Wolfe effect. And it tells us not only about where matter once clumped, but also about how dark energy stretches the universe today. Meanwhile, the original Sachs-Wolfe effect, also known as the ordinary version, happens at the moment of recombination, where photons are redshifted or blueshifted depending on the gravitational potential they were born into. In both cases, gravity acts not as a sculptor of matter, but as a warper of light, leaving behind a signature on the ancient sky. This gravitational redshifting doesn't create huge patterns or obvious imprints. It produces temperature variations in the CMB on the order of microkelvins, tiny deviations from the average temperature of 2.725 Kelvin. But these small changes carry vast meaning. By mapping the angular scale of these fluctuations across the sky, cosmologists can reconstruct the structure of the early universe and test theories of general relativity, inflation, and the nature of dark energy. The Sachs-Wolfe effect, therefore, is more than a curiosity. It is a window into the interplay between light and gravity in the expanding cosmos. It reveals how gravity doesn't just pull on mass, but also sculpts the very fabric through which light travels. And in a universe governed by Einstein's equations, this interaction is not only allowed, it's inevitable. To visualize this, Imagine a photon as a skier crossing a hilly landscape. As it descends into a gravitational valley, it picks up speed, it gains energy, but as it climbs out, it slows, losing what it gained. In a static universe, this would cancel out, down, then up, gain, then loss. But in our expanding cosmos, the hills flatten as the skier climbs, meaning the climb is less steep than the descent. The photon doesn't lose all the energy it gained, so it arrives slightly hotter. Conversely, if it starts on a peak that flattens, as it leaves, it ends up colder. This dynamic reshaping of space changes the photon's fate. And when millions of such photons from different regions arrive together, their collective shifts create a map of hot and cold spots in the CMB. The Sachs-Wolfe effect is, in essence, the memory of how the landscape changed while light was en route. Why is this important? Because this effect only arises if the gravitational potential evolves over time, which requires something more than matter alone. It requires dark energy in a universe. Without dark energy, the gravitational wells remain stable. They don't change enough to create the Sachs-Wolfe imbalance. But the fact that we observe the effect, especially at large angular scales, tells us the universe is not only expanding but accelerating. In other words, gravity's fingerprint on the CMB confirms something astonishing, that some unknown energy is stretching the fabric of space faster and faster, pushing galaxies apart and reshaping the cosmic terrain. The Sachs-Wolfe effect, then, is not just a relic of the past. It is a probe of the present, a test of the future, and a confirmation of dark energy's mysterious hand. But there's another twist. This signal is incredibly hard to detect. The original Sachs-Wolfe effect is buried in the primordial CMB, tangled with other temperature fluctuations caused by quantum inflation, acoustic oscillations, and the random noise of early plasma. The integrated Sachs-Wolfe effect is even subtler. It only appears at the largest scales and requires cross-correlation with galaxy surveys to become visible. In practice, cosmologists map the positions of galaxies in the sky, tracing the large-scale structure of matter, and compare that to the temperature variations in the CMB, where galaxies cluster. Photons should have passed through deeper gravitational wells. If the temperature of the CMB is slightly warmer in those regions, that's the Sachs-Wolfe effect in action. It is like seeing the shadows of mountains, not from the light they cast, but from the way sound echoes around them. This means that by studying this effect, we can link the early universe to its current structure. We can test whether gravity behaves according to Einstein's predictions, or if something new is at play. Some alternative gravity theories, like those modifying general relativity at cosmic scales, predict different Sachs-Wolfe signatures. So far, the data has agreed with dark energy and general relativity. But the game is far from over. Future missions with more precise measurements, like those planned for the next generation of space telescopes, may reveal deviations or surprises. Perhaps there are subtle anisotropies we've missed, or unknown forces at work in the cosmic expansion. The Sachs-Wolfe effect, though delicate, may become one of our sharpest tools to probe these mysteries. At a deeper level, this effect is a reminder that gravity isn't just a force, it's a geometry. When we say a photon is redshifted by gravity, what we're really saying is that space itself has changed underneath it. The photon's wavelength isn't altered by some external pull, but by the stretching or compressing of the spacetime through which it moves. This is Einstein's vision made real. Light follows the straightest possible path through a curved universe, and in doing so, it reveals the shape of that curvature. The Sachs-Wolfe effect lets us hear the change in that shape across billions of years. Not with our ears, but with our instruments. It's gravity whispering to us through the light of the past. So when you look up at the sky and think of the stars and galaxies scattered across its dome, remember that the darkness between them is not empty. It is filled with ancient light, cold and quiet, carrying the echo of gravity's earliest voice. That echo, the Sachs-Wolfe effect, isn't loud or flashy. It's a murmur in the margins, a bending of brightness by invisible hands. And yet, from that murmur, we learn about the universe's growth, its age, its contents, and its fate. We learn how light remembers the places it passed through, and we learn, most astonishingly, that even gravity, so often thought of as mute, can leave behind a message in the light, not through motion, but through distortion, not through sound, but through silence stretched across space. The Sachs-Wolfe effect is gravity's subtle monologue, delivered not with words, but with warmth and coldness, imprinted on the cosmic canvas. A final reminder that in the vast theatre of the cosmos, even the quietest forces have stories to tell, if only we learn how to listen. Magnetars. When magnetic fields become monstrous forces, not every cosmic monster announces itself with fire. Some whisper their power through magnetism, so intense it bends atoms, warps space, and cracks stars from the inside out. These are magnetars, the most magnetic objects in the known universe, born from the death of massive stars, but transformed into something far stranger than a typical neutron star. While most stellar corpses quietly fade into dense but stable remnants, a rare few are forged under such extreme pressures and rotational chaos that their very fabric becomes unstable, generating magnetic fields 1,000 trillion times stronger than Earth's. To put it in perspective, if a magnetar were placed halfway across the moon, it could erase every credit card on Earth and tear iron from your blood. These are not just dense stars, they are cosmic pressure cookers of magnetism, where the structure of matter itself begins to break down under the force of their invisible grasp. In the core of a magnetar, atomic nuclei are crushed into neutron matter. But the magnetic field doesn't just sit quietly. It twists, it strains, it builds, until the crust of the star literally snaps, releasing gamma ray flares so powerful that even from tens of thousands of light years away, they can blind satellites and disturb Earth's upper atmosphere. These starquakes are not science fiction. They are real, observed events that remind us how violent and alien the universe can be, even in total silence. Magnetars begin their lives as ordinary massive stars, those that are more than 8 to 10 times the mass of the Sun. As these stars age, they burn through their nuclear fuel and can no longer resist the pull of their own gravity. The result is core collapse. The heart of the star implodes, while outer layers are blasted away in a supernova, but under very specific and extreme conditions, perhaps linked to rapid rotation or strong seed magnetic fields in the progenitor star. The collapsing core doesn't just become a typical neutron star. Instead, it spins up into a hyper-energized object, amplifying its magnetic field to unimaginable levels. This field is what defines a magnetar, a neutron star with a magnetic field exceeding 10 to the power of 14, or even 10 to the power of 15 Gauss. For comparison, Earth's magnetic field is around 0.5 Gauss. Even the strongest man-made magnets barely touch 10 to the power of 5 Gauss. A magnetar is so magnetic that it can distort electron orbitals in atoms and create forces that rival or exceed gravity itself within a few kilometers of its surface. At that point, we're no longer dealing with normal matter. We're in the realm where quantum electrodynamics and general relativity begin to clash, where the vacuum itself can become unstable, spawning virtual particles and bizarre quantum behavior in a regime we can't reproduce on Earth. These magnetic fields aren't static either. The interior of a magnetar is like a tangled bundle of magnetic stress, slowly evolving, twisting, and accumulating tension over years or decades. Occasionally, this tension becomes too great, and the crust of the magnetar, a thin but incredibly dense layer of neutron-rich matter, suddenly cracks. This fracture releases a burst of energy equivalent to hundreds of thousands of Earth's nuclear arsenals exploding at once. These outbursts are detected as soft gamma repeaters or anomalous X-ray pulsars, both of which are classes of magnetars, identified by their erratic, high-energy emissions. In 2004, One such flare from a magnetar, 50,000 light years away, passed through the solar system, briefly becoming the brightest object in the gamma-ray sky after the Sunday and ionizing Earth's upper atmosphere. If such a flare occurred within just a few light years of Earth, it could disrupt satellites, damage electronics, and even pose risks to biological life. Fortunately, magnetars are rare, and the closest known one is far enough to pose no immediate threat. But their very existence is a reminder of how little we truly control in the cosmos. Their rarity, in fact, is one of their most intriguing aspects. Out of the hundreds of billions of stars in our galaxy, we've identified only a few dozen magnetars. This suggests that the conditions required to create one are extremely precise, perhaps involving not just mass, but rotational speed, metallicity, and binary interactions. Some researchers believe that certain superluminous supernovae and long gamma-ray bursts may be powered by newly formed magnetars, spinning down as their magnetic fields convert rotational energy into electromagnetic radiation. In these models, the magnetar acts like a cosmic dynamo, losing energy at a furious rate and lighting up its surroundings with a brilliance that outshines entire galaxies for a few seconds. Others propose that magnetars might be the source of mysterious fast radio bursts, brief millisecond-scale radio signals coming from distant galaxies. In fact, in 2020, a fast radio bursts was detected from within our own Milky Way for the first time, and it was traced back to a known magnetar. This potential link between magnetars and fast radio bursts could open a new window into understanding not just extreme magnetic phenomena, but the broader astrophysical processes that shape galaxies and interstellar space. And yet, despite the intense focus magnetars receive, we still don't fully understand their inner workings. What sustains such immense magnetic fields? Why do they decay so quickly compared to ordinary pulsars? How do they interact with their environment in the long term? Over time, the magnetic field of a magnetar gradually weakens, converting energy into heat and X-ray emission. Eventually, it may settle into a more ordinary neutron star state, but not before shedding enormous amounts of energy. Some theoretical models suggest that as magnetars cool and their magnetic fields fade, they may experience a kind of magnetic death, falling silent and becoming nearly undetectable. Others speculate that they could collapse into black holes if they lose rotational support or accrete too much mass. There's even the question of how their magnetospheres, the regions dominated by their magnetic fields, behave. These zones are likely filled with ultra-relativistic particles, twisted field lines, and regions where exotic plasma physics takes place. Understanding a magnetar's magnetosphere might not only teach us about stellar remnants, but could help explain conditions in other extreme environments, such as the early universe or the vicinity of black holes. Perhaps what makes magnetars so compelling is not just their raw power, but their paradoxical nature. They are both dead and alive, collapsed and dynamic, silent and explosive. From the outside, they may look like small, faint points of light in X-ray or gamma-ray maps, but inside, they are burning with magnetic tension, teetering on the edge of rupture. Their magnetic fields can trap light, generate particle storms, and even alter the vacuum of space. In their most extreme states, they challenge the boundaries of physics, pushing us to reconcile quantum theory with general relativity. Magnetars are not just astrophysical curiosities. They are laboratories of fundamental physics, offering glimpses into regimes we cannot replicate on Earth. They test our models, stretch our theories, and whisper of forces that were born in the early seconds of the universe and still echo in the present. So next time you hear about magnetic fields, whether it is the gentle one protecting your planet or the one behind a refrigerator magnet, remember that somewhere out there, in a quiet corner of the galaxy, a star-sized corpse is spinning slowly, wrapped in magnetic fury so intense that even atoms themselves cannot stay intact. It does not shine like a sun or roar like a black hole, but waits in eerie silence, occasionally trembling and releasing pulses of unimaginable energy into the void. That's a magnetar, a monument to the strange possibilities of stellar death, and a humbling reminder that in the vast darkness of space, power sometimes wears a quiet face. Primordial gravitational waves, the faint echo of creation itself. What if the earliest memory of the universe isn't a picture, but a ripple? An ancient wave still moving through space-time, carrying with it the silent echo of existence's first breath. Long before galaxies took shape, before atoms formed, even before light could travel freely, something stirred the very structure of reality. Not energy in the way we know it, not particles or heat, but a tremor, a stretching and squeezing of space-time itself, like the trembling of a cosmic drumhead struck by the raw violence of the Big Bang. These are primordial gravitational waves, ghost-like oscillations born not from black holes or colliding stars, but from the very birth of the universe, when space-time was still molten and chaos reigned supreme. Unlike electromagnetic radiation, which interacts with matter and fades, these waves are nearly untouched by the billions of years since their creation. They've passed through everything, through the formation of galaxies, through the creation of atoms, through all of history, without scattering or slowing, silent messengers of an origin we can only begin to grasp. To detect them is to hear the whisper of creation itself, to reach beyond light and into the very bones of reality, and to glimpse the conditions that existed when time and space were newborn. Understanding these waves requires us to step into a time so early, so dense, that all of physics as we know it begins to blur. During the first tiny fraction of a second after the Big Bang, specifically around 10 to the power of -36 seconds, cosmologists believe the universe underwent a period of rapid, exponential expansion called inflation. This wasn't ordinary expansion, like a balloon slowly inflating. It was explosive, faster, fan, light expansion, driven by vacuum energy, stretching microscopic quantum fluctuations to cosmic scales. These quantum jitters, present in all fields, including the gravitational field, were frozen in place by the expansion, imprinted into the very fabric of space-time as gravitational waves. Unlike density fluctuations that would later seed galaxies, these gravitational waves didn't clump matter. They simply disturbed space itself, moving outward forever. The result is a background hum, a relic noise from the beginning, not in sound but in rhythm, rippling through the universe with wavelengths so vast that even detecting them requires instruments capable of measuring changes smaller than a proton's width across distances the size of Earth, or larger. But what makes primordial gravitational waves different from other gravitational waves, the ones detected by observatories like LIGO and Virgo, is not just their age, but their origin. Whereas LIGO's waves come from cataclysmic events, like merging black holes or neutron stars, these primordial waves were not created by motion within the universe. They were created by the universe itself. In motion, they are not secondary effects. They are primary. They are not echoes of structure, but echoes of emergence, and their signature is subtle. So subtle that we can't detect them directly with current gravitational wave detectors. Instead, we search for their imprint on the oldest light we can see, the cosmic microwave background. As these waves passed through the universe during the epoch of recombination, when photons first began to travel freely, they left a faint twisting pattern on the polarization of that light, known as B-mode polarization. Detecting this pattern would not only confirm inflation, but reveal its specific nature, what field drove it, what energy scale it operated at, and whether quantum gravity effects played a role. It would be, in essence, a direct line of communication from the birth of space-time itself. But this detection is maddeningly difficult. The B-mode, signal from primordial gravitational waves, is expected to be extraordinarily faint, easily drowned out by foreground effects from dust in our galaxy or other cosmic phenomena. In 2014, the BICEP-2 experiment announced a detection of B-mode polarization, sending ripples of excitement through the physics community. But further analysis showed that galactic dust accounted for much of the signal. Still, the search continues. With experiments like the Simons Observatory, Lightbird, and CMBS-4 on the horizon, each designed with higher precision and greater control over noise, the stakes are enormous. Confirming the presence of primordial gravitational waves would not only solidify inflation as the correct model of the early universe, but would also allow us to test ideas from quantum gravity, such as string theory or loop quantum cosmology. It would push physics into a new regime, one we've never experimentally accessed, where space-time is no longer a passive arena, but an active, fluctuating entity, jittering with energy, even in its calmest state. These waves also force us to re-evaluate our assumptions about beginnings. In most physical systems, we can examine a cause and observe its effect. But with the Big Bang, we are trapped at the edge of understanding. Primordial gravitational waves offer a rare exception, a cause without a visible source, but with an effect that persists to this day. They are evidence that quantum mechanics and general relativity, two theories that usually clash, once worked together in shaping the universe. The mere fact that quantum fluctuations in gravity could stretch across billions of light years and remain coherent enough to be measured is astonishing. It implies that space-time itself had a quantum character in its infancy, a trembling, probabilistic texture that resolved into the smooth cosmic expansion we see today. And if these waves can be measured, we may even be able to distinguish between different models of inflation, telling us whether the early universe was dominated by a simple scalar field, a complex landscape of interacting fields, or even phenomena we haven't yet imagined. There's also a philosophical weight to these waves. They are not part of the visible universe, not stars, or galaxies, or radiation. They are part of the structure of the universe, moving invisibly through us at every moment. Evidence of something that once happened to space itself. They don't carry information in the traditional sense. They are the information. They're not like fossilized light, but more like fossilized motion, preserved across cosmic time. When we talk about hearing the universe's first sound, what we really mean is detecting the vibration of its birth. Like listening not to a baby's first cry, but to the tremor in the crib from which the baby emerged. It's humbling to realize that such tremors could still be passing through you right now, gently stretching and compressing your body in ways that are far too small to feel, but massive in implication. You are, right now, a participant in a cosmic story that began long before Earth formed, and you're being moved ever so slightly by a memory older than time. These waves could even help explain the multiverse. Some models of inflation suggest that our universe is just one bubble in a frothing sea of universes, each with its own laws of physics, its own constants, its own fate. In this chaotic inflationary landscape, primordial gravitational waves may carry imprints of collisions with other bubbles or features of the inflating field itself. If detected, specific deviations in the spectrum or polarization of these waves might suggest not just a single inflating universe, but an ensemble of them. This is speculation, yes, but scientifically grounded speculation, guided by predictions that can be tested. In this way, gravitational waves may become not just a tool for cosmology, but a bridge between metaphysical questions and physical measurements, a path toward reconciling the philosophical with the empirical. And even if we never find them, the very search has revolutionized our understanding of the cosmos. The technological innovations required, ultra-sensitive detectors, deep space telescopes, cryogenic cooling, precise modeling of cosmic dust, have pushed the boundaries of what we can observe and how we can observe it. We are now able to model the universe, not just as a collection of objects, but as a dynamic living field of interactions and waves. In this view, the universe is not static or dead, but alive with tremors, stretching and rebounding, echoing with the rhythms of its own becoming. It suggests that what we call the void, the emptiness between galaxies, is anything but empty. It's a medium, a canvas, a vibrating scaffold upon which the story of matter and energy is painted. So when you close your eyes and imagine the beginning of everything, not just a flash, but a feeling, consider that somewhere out there, and also right here, those first moments are still moving through you. They remember a time when the universe was younger than a fraction of a second, when dimensions themselves may have fluctuated, when everything we now call real was still potential. To find them is to shake hands with the origin, to touch something before light, before atoms, before time itself had rhythm. And whether or not we succeed, the effort itself changes us, because it proves that we can ask questions that stretch across the ages, and that even the faintest echo, when heard clearly, can rewrite the meaning of existence. Galactic halos, the vast spheres of influence around every galaxy. You might think a galaxy ends where its stars fade into darkness, but that's an illusion born from light, not from gravity. And in the silent architecture of the universe, what's invisible often outweighs what's seen. Surrounding every galaxy like an enormous, ghostly aura is something vast, spherical, and utterly essential: the galactic halo. This isn't a glowing ring or a luminous veil. It's a sprawling, nearly invisible structure that extends far beyond the glittering disk of stars, wrapping galaxies in a shroud of influence that defies ordinary boundaries. Galactic halos are made not of light, but of mass, filled with ancient stars, ionized gas, and most intriguingly, dark matter. They are gravitational cocoons, defining the real size, motion, and future of galaxies. And they contain far more mass than the galaxies themselves. When we look up at the Milky Way and see its sparkling spine stretched across the sky, we're seeing only the center of something much grander. Our galaxy's true size is many times wider, defined not by what emits photons, but by the silent, spherical halo that encircles it. And the deeper we study these halos, the more we realize they are not just galactic accessories. They are galactic foundations, revealing truths about how galaxies form, how they evolve, and what unseen forces hold the universe together. At the heart of every galactic halo lies a paradox. It shapes everything, yet hides from sight. For decades, astronomers noticed a strange discrepancy. The outer stars of galaxies orbit far too quickly to be held by visible matter alone. According to Newtonian physics, stars near the edge of a galaxy should orbit more slowly, just like planets in the outer solar system. But that's not what happens. Instead, galactic rotation curves remain flat, implying that some hidden mass, an invisible scaffold, must be exerting gravitational pull. This discovery, first made by Vera Rubin and others in the 1970s, was one of the earliest and most compelling pieces of evidence for dark matter. And where does this dark matter reside in the halo? The galactic halo, therefore, isn't just a dusty shell. It's the dominant mass component of galaxies, the glue that binds them, the force that shapes their rotation, their mergers, and their evolution over billions of years. While the luminous disk contains the stars and gas we can observe, the halo is the gravitational anchor that ensures galaxies don't fly apart. Without it, the elegant spiral arms of the Milky Way would unravel, and the structure of the cosmic web would collapse into chaos. But halos are not just containers for dark matter. They're also homes to some of the oldest stellar populations in the universe. These are the halo stars, ancient, metal-poor relics from the earliest days of galaxy formation. Unlike the relatively young stars in the galactic disk, halo stars often follow eccentric, inclined orbits, suggesting they may have originated in smaller galaxies that were consumed and assimilated. Their chemistry tells a story of a simpler cosmos, unpolluted by generations of supernovae. In fact, by studying the motion and composition of halo stars, astronomers can reconstruct the merger history of a galaxy, essentially performing galactic archaeology. Some stellar streams found in halos are remnants of long-disrupted dwarf galaxies or globular clusters, stretched into arcs by tidal forces. These rivers of stars whisper the history of cosmic cannibalism, where large galaxies grew by devouring smaller ones, and their trails remain as scars across the halo. even more mysterious, is the halo's gaseous component. A vast reservoir of ionized hydrogen, often hundreds of thousands of light years across. This circumgalactic medium is a dynamic and critical part of galactic life. Though nearly invisible in optical wavelengths, it can be detected through absorption lines in the spectra of distant quasars, or through faint X-ray emissions. The circumgalactic medium acts as both a fuel tank and a recycling plant. It provides raw material for star formation by funneling gas into the galactic disk, and it also receives gas blown out by stellar winds, supernovae, and active galactic nuclei. This feedback loop regulates the growth of galaxies, preventing runaway star formation and maintaining equilibrium over billions of years. In some ways, the halo is a galaxy's lungs, exchanging gases with its environment, breathing in cold flows from intergalactic space, and exhaling enriched material from its core. Without this invisible exchange, galaxies would quickly run out of gas and cease to evolve. Understanding the circumgalactic medium, therefore, is not a niche pursuit. It's central to understanding galactic ecology. Dark matter, old stars, and ionized gas are not the only components of galactic halos. Increasing evidence suggests they may also harbor magnetic fields, cosmic rays, and even rogue planets or failed stars. The magnetic fields in halos are difficult to detect, but may play a role in guiding the movement of charged particles or shaping the flow of gas. Cosmic rays, high-energy particles accelerated by supernova shocks or black hole jets, can escape the galactic disk and populate the halo, where they may influence thermal balance or gas dynamics. These layers of complexity turn the halo from a simple shell into a rich, multi-phase environment where astrophysical processes unfold on enormous scales. It is not just the outskirts of a galaxy, it's a frontier of physics, where gravity, thermodynamics, magnetism, and particle acceleration intersect. And yet, for all we know, halos remain elusive. We can't photograph them directly. We infer their existence from motion, from faint emissions, from distortions in starlight and quasar spectra. They're like cosmic weather patterns, huge dynamic, but only perceptible through their effects. Simulations suggest that halos may even contain substructures, dark matter clumps, or mini-halos, that never formed stars, but still influence gravitational behavior. These subhalos might be responsible for gravitational lensing anomalies, or for heating thin stellar streams into broader ribbons. If we could map these dark substructures, we might finally unlock the true distribution of dark matter and test competing theories. Whether it is made of weakly interacting particles, axions, or something even more exotic. In galaxy clusters, halos extend even further, overlapping and interlocking like soap bubbles in a cosmic foam. Here, they contribute to the intracluster medium, a hot, X-ray emitting gas that fills the space between galaxies and binds the cluster together. In this context, halos are not isolated structures, but part of a continuum, forming the backbone of the large-scale structure of the universe. The cosmic web itself, those vast filaments of matter connecting galaxies across hundreds of millions of light years, is shaped and sustained by the cumulative influence of halos. The interaction between halo and halo, between gravity and gas, is what drives cosmic evolution at every level, from dwarf galaxies to superclusters. Perhaps most striking is what halos reveal about our place in the cosmos. We live in a disk, a bright, thin ribbon of stars rotating around a central bulge. But we are surrounded by a much vaster, darker environment. An ocean in which we float. That halo, largely invisible, defines the gravitational boundary of our galaxy. It determines how fast we orbit the center, how long it takes light to escape, and how galaxies interact with one another. The Andromeda Galaxy has a halo too, and simulations suggest that our halos have already begun to touch, intertwining at their edges, even though our stellar disks are still 2 million light years apart. In a few billion years, these two halos will guide their galaxies into a colossal merger, birthing a new galaxy and reshaping local space forever. It is not the stars that dictate this encounter. It is the unseen spheres surrounding them, quietly shepherding their motions. So the next time you look at a galaxy, whether it's a photograph of Andromeda, a spiral captured by Hubble, or the smear of the Milky Way across your night sky, remember that what you see is only the core of a far larger presence. Beyond the stars, beyond the glow, beyond what our eyes can detect, lies a vast and vital structure shaping every movement, every interaction, every moment in the life of a galaxy. The galactic halo is not just a boundary. It is a domain, a memory, a scaffold, a mystery, and within its darkness lies not emptiness, but influence, quiet, invisible, and essential. Anisotropy in the universe. When cosmic symmetry breaks quietly, what if the most profound truths of the universe aren't hidden in noise or chaos, but in the tiniest irregularities, the gentlest imperfections, the quietest whispers of asymmetry in what we assumed was flawless? For centuries, we've sought the grand design, a cosmos governed by elegance, uniformity, and balance. But as we've peered deeper into the fabric of space, a strange realization has emerged. The universe isn't perfectly symmetrical, and it's in this subtle breaking of cosmic symmetry, in the patterns that don't quite match, that the universe's history, structure, and destiny reveal themselves. This subtle unevenness, this anisotropy, isn't a flaw, it's a fingerprint. To understand it, we must first visit one of the most sacred pillars of modern cosmology, the cosmological principle. This idea holds that the universe, on large enough scales, is both homogeneous and isotropic. It's a comforting thought that there's no special direction, no cosmic bias, no preferred vantage point. And for the most part, it holds true, but not entirely. The cosmic microwave background, that afterglow of the Big Bang, that ancient light stretched thin by time, carries with it the story of a universe once hot, dense, and smooth. Yet when we measure the temperature of this light from every direction, we find minute variations, subtle temperature shifts at the level of microkelvins. These aren't random fluctuations. They're structured, they have scales, they form maps. And from those maps, we can read the universe's deepest secrets. Anisotropy is not just an observational detail. It is a foundational phenomenon. The tiny temperature differences in the cosmic microwave background represent quantum fluctuations stretched across the cosmos during inflation, a mind-bending event just fractions of a second after the Big Bang, when space itself expanded exponentially. Imagine quantum blips frozen into existence and then ballooned into galactic proportions. Those frozen ripples became the seeds of structure, the origins of galaxies, clusters, filaments, and voids. Without anisotropy, the universe would remain a featureless fog. Symmetry breaking, in this sense, is what allows complexity to emerge. But there's more. These anisotropies aren't just random. They display alignments and hemispherical differences that have puzzled scientists for decades. For example, the so-called axis of evil, a term coined half-jokingly, refers to a surprising alignment of temperature multipoles in the cosmic microwave background, suggesting a possible preferred direction in space. If confirmed, this would violate isotropy at a fundamental level. It would mean the universe does have a bias, a direction baked into the very structure of space-time. And if that's true, we have to ask what caused it. Could the early universe have been shaped by exotic physics, anisotropic inflation, topological defects, or relic gravitational waves? Could we be living in a universe that had a spinning phase, or one connected to other universes through cosmic strings that pulled and twisted the early plasma into subtle asymmetries? Or are these merely statistical anomalies, coincidences magnified by our desire to see meaning in the noise? The debate is ongoing, but even outside the cosmic microwave background, Anisotropy plays a critical role. The distribution of galaxies, though roughly uniform at the largest scales, still shows preferential clustering along filaments and walls, forming the cosmic web, a structure that would not exist without early anisotropies. Observations of galaxy spins, large quasar groupings, and polarization of light from distant sources sometimes hint at alignments that challenge the assumption of isotropy. And while these observations remain tentative, they invite a radical possibility that symmetry is not the default. It is the exception. Even in physics, we see this pattern repeated. The laws of nature favor certain particles, directions, and interactions. Weak nuclear force violates parity. CP violation hints at a universe that prefers matter over antimatter. Chirality in amino acids suggests asymmetry runs deep into biology. Could these be reflections of a deeper cosmological asymmetry? Could the breaking of symmetry be the key that turns simplicity into life, uniformity into beauty, nothing into something? Anisotropy may be the universe's way of writing complexity into its own code, but it's not just about science, it's about philosophy. Because if the universe isn't the same in all directions, then the idea of cosmic neutrality dissolves. There may be a direction in the sky that truly is special, a cosmic north that predates galaxies and stars, an echo of an earlier time when the universe remembered its birth orientation. And that changes how we think about everything: our place, our motion, our uniqueness. In everyday life, we assume symmetry is ideal. In faces, in buildings, in art. The universe didn't evolve because it was perfect, but because it wasn't an isotropy in this sense, is the crack through which evolution flows. From a physics standpoint, detecting and interpreting anisotropy requires exquisite precision. Satellites like COBE, MAP, and Planck have mapped the cosmic microwave background with increasing detail, allowing us to reconstruct the universe's initial conditions with staggering fidelity. But with greater precision comes greater mystery. Certain patterns resist explanation. Low quadrupole moments, hemispheric power asymmetry, and anomalous cold spots continue to invite interpretations that range from instrumental artifacts to signals of multiverse collisions. Yes, multiverse, because some inflationary models predict that our universe may be just one bubble among many. And if two such bubbles collided, the imprint might appear as an anisotropic scar in the cosmic microwave background. Could that cold spot in the southern hemisphere be the bruise left by another universe? It sounds outrageous, and it is. But so did cosmic expansion, dark energy, and quantum entanglement once. The history of science is a history of ideas that were too strange to believe until they weren't. Anisotropy might be the next doorway. And if we walk through it, we may discover that the universe's asymmetry is not a blemish, but a signature, a message left in the geometry of space that says, I am not uniform, I am not blind, I remember. It teaches us that beauty lies not in sameness, but in variation, that a perfectly smooth cosmos would be lifeless, and that the flickers, swirls, and tiny asymmetries are what allow meaning, structure, and consciousness to arise. The universe doesn't need to shout to be profound. Sometimes it simply nudges, and in that nudge, in the almost imperceptible unevenness of the sky, it whispers the story of everything. Cold, dark gas, the invisible fuel of star formation. Not every ingredient of cosmic creation shines. Some remain cloaked in darkness, hidden even from the most sensitive telescopes, yet quietly shaping the birth of stars and the destiny of galaxies. This is the strange realm of cold, dark gas, a component so elusive that it escapes detection not because it's rare, but because it refuses to glow, absorbing and emitting virtually no light. Unlike the bright nebulae we see in photographs, those glowing clouds of ionized hydrogen that cradle newborn stars, cold, dark gas is invisible to optical instruments, veiled in temperature and obscurity, yet it makes up much of the raw material from which stars are born. It lingers in the outskirts of galaxies, in the arms of spirals, in vast filaments connecting cosmic structures, It hides in the shadows where light cannot reach, preserving the quiet density and low temperatures needed to form the gravitational seeds of stellar nurseries. And while it may never announce its presence through brilliant color or luminous shockwaves, its silence is precisely what gives it power. Because in that silence, the universe begins again. To understand the role of cold, dark gas, we must first unlearn a visual bias, our instinct to equate brightness with importance. Star formation doesn't begin in shining gas. It begins in the darkest corners, where clouds of molecular hydrogen become so cold and dense that they begin to collapse under their own weight. The paradox is that hydrogen, the most abundant molecule in the universe, and the primary constituent of cold gas clouds, does not emit easily detectable radiation at low temperatures. It is practically invisible to optical and even many infrared instruments, meaning astronomers must infer its presence indirectly, through the behavior of tracer molecules like carbon monoxide, through dust absorption in starlight, or through subtle radio emissions from rare interactions. But these methods only scratch the surface. In low metallicity environments, such as the outskirts of galaxies or in dwarf galaxies, even these tracers may fail. This leads to the hypothesis that vast quantities of carbon monoxide dark, or even completely dark molecular gas may exist undetected, representing a significant hidden component of the star, forming reservoir of the cosmos. In essence, we are navigating an ocean of star, forming fuel with only glimpses of its waves. This invisible gas plays a critical role in the galactic ecosystem. It serves as the initial condition for the gravitational collapse that leads to star formation, acting as a cold, pressureless medium ripe for fragmentation. When a region within a cloud becomes dense enough, it can collapse inward, forming protostars that eventually ignite fusion in their cores. But this process is highly sensitive to temperature, pressure, turbulence, and magnetic fields. Cold gas is especially efficient at collapsing because its low temperature means less internal pressure resisting gravity. The colder the cloud, the easier it is for small perturbations to grow, allowing gravity to dominate. This is why understanding where cold gas resides, how it flows, and how it accumulates is essential to predicting where and when stars will form. It's not enough to see the stars after they emerge. We must uncover the hidden currents that feed them. Observationally, this challenge has driven astronomers to design increasingly sophisticated instruments and methods. Radio telescopes like ALMA, the Very Large Array, and future missions like the Square Kilometre Array aim to detect the faint whispers of molecular transitions and continuum emissions from dust that betray the presence of cold gas. In nearby galaxies, astronomers use velocity maps of neutral hydrogen to identify cold regions, or compare infrared dust maps with carbon monoxide distributions to infer dark gas regions. Even in the Milky Way, where we have detailed access to molecular clouds, the full extent of cold dark gas remains uncertain. Recent surveys combining gamma ray observations, dust emission, and molecular line tracers have revealed large reservoirs of dark gas not accounted for in traditional models. In some regions, this hidden component may rival or even exceed the mass of known gas clouds, suggesting that we may have significantly underestimated the universe's star-forming potential. But cold dark gas is not just a passive supply. It's a dynamic participant in galactic life. It can be influenced by supernova shocks, spiral arm compression, tidal interactions, and cosmic inflows from the intergalactic medium. When galaxies collide or pass near each other, their halos and disks interact gravitationally, compressing gas and triggering massive starbursts. Yet these dramatic events often rely on pre-existing reservoirs of cold gas. Without it, even the most violent galactic collisions would produce little more than heat and chaos. On smaller scales, turbulence within molecular clouds can both trigger and suppress star formation, creating a chaotic balance between gravitational collapse and internal motion. Magnetic fields can thread through these clouds, supporting them against collapse or guiding the flow of gas into filaments. Understanding the dynamics of cold gas is therefore not a secondary detail. It's the key to understanding why galaxies look the way they do. Cold dark gas also plays a role in cosmic feedback loops. As stars form and evolve, they inject energy back into their surroundings through radiation, stellar winds, and eventually supernova explosions. This energy can heat surrounding gas, disperse clouds, or compress nearby regions, creating a patchwork of triggered and quenched star formation. But the extent to which this feedback reaches depends on the structure and temperature of the surrounding gas. Cold gas can absorb and contain this energy, channeling it into motion or turbulence rather than heat. In this way, it shapes the efficiency of star formation, determining whether a galaxy produces stars in a gentle drizzle or in explosive bursts. Some galaxies, like low-surface, brightness galaxies, are dominated by cold gas but form stars inefficiently, suggesting that other factors, like metallicity or stability, play roles in regulating the transition from gas to star. Others, like starburst galaxies, burn through their cold gas rapidly, producing clusters of stars in short, intense episodes. The presence and distribution of cold dark gas also carry implications for galaxy evolution across cosmic time. In the early universe, galaxies were smaller, more irregular, and often rich in cold gas. The high gas fractions of these primordial galaxies fueled rapid star formation. Contributing to the peak of cosmic star formation around redshift Z is approximately 2, known as cosmic noon. As galaxies aged, they converted more of their gas into stars, or lost it to outflows and environmental effects like ram pressure, stripping in clusters. Today, many massive galaxies are gas-poor, especially in their centers, while smaller or isolated galaxies may still retain significant cold gas reservoirs. Tracking this transformation requires mapping the cold gas content of galaxies across different epochs, revealing how they fuel themselves, age, and die. Beyond galaxies, cold gas also populates the cosmic web. In the filaments connecting clusters and groups, simulations suggest that cold gas can exist in thin streams, funneled by gravity toward galactic halos. These cosmic inflows may supply galaxies with fresh material long after their initial formation, sustaining star formation for billions of years. Detecting such inflows remains challenging, but new techniques involving Lyman, alpha absorption, X-ray shadows, and Sunyaev-Zeldovich distortions may soon reveal their presence. If confirmed, these streams would represent the hidden arteries of the universe, feeding galaxies from a vast, unseen network of cold, diffuse matter. What makes cold, dark gas so intellectually and philosophically compelling is the idea that the engine of creation can operate in near total silence. The stars that light our skies owe their existence not to what we can see, but to what lurks just beneath detection, to the quiet, patient gathering of atoms in darkness. We like to think of cosmic activity as dramatic, explosive, and radiant, but the universe's most essential work, building stars, shaping galaxies, forging the conditions for life, often happens in stillness, hidden beneath thresholds of light. Cold dark gas is the cosmic womb, the stage upon which light rehearses its entrance, and without it, the universe would be a sterile void. So the next time you see an image of a newborn star or a glowing nebula, remember that behind the brilliance lies a deeper, colder reality, one that never asked to be seen, but without which none of it would exist. Cold dark gas doesn't seek attention. It doesn't shine or scream. It simply waits until gravity calls, and the next generation of stars ignites from its quiet depths. It is the invisible fuel of creation, and through its darkness, the universe learns how to shine. Shear mapping. How astronomers reconstruct invisible forces. Sometimes the universe reveals its secrets, not through brightness or motion, but through distortion. Subtle, systematic warps in the way galaxies appear, like a cosmic fingerprint, etched not by what we see, but by what lies hidden between us and them. This is the silent language of shear mapping, a powerful technique in modern cosmology that allows astronomers to detect the invisible scaffolding of the cosmos, by studying how light is ever so slightly bent as it travels through space. It's not about photographing objects directly, but about decoding the distortions imprinted on their images by gravitational lensing, tiny stretches and compressions caused by massive structures warping spacetime itself. Unlike strong lensing, where galaxies appear dramatically warped into arcs and rings, shear mapping deals with weak lensing, so faint and delicate that the distortions are often smaller than the width of a pixel. Yet when applied statistically to millions of galaxies across the sky, a pattern emerges, a map of gravitational influence, revealing where dark matter clumps, how structures grow, and how the fabric of space-time stretches across billions of light years. In this realm, gravity becomes a lens, and galaxies become test particles, scattered across the sky not just as they are, but as shaped by the weight of the invisible. To grasp the elegance of shear mapping, you have to understand the concept of weak gravitational lensing. As light from distant galaxies journeys toward us, it passes through regions of the universe filled with matter, both luminous and dark. According to Einstein's general relativity, mass bends space-time, and light follows these curves, like a marble rolling along a warped surface. The result is a slight distortion in the shape of background galaxies. They appear stretched along the direction perpendicular to the mass concentration. These distortions, called shear, are tiny, far smaller than anything you'd notice looking at a single galaxy, but when measured across vast areas of the sky, they allow cosmologists to infer the distribution of mass, even when that mass emits no light at all. By averaging the shapes and orientations of galaxies in different parts of the sky, astronomers construct a shear field which can be used to engineer the underlying mass distribution, a process known as mass reconstruction. This is the heart of shear mapping, using the delicate imprint left by gravity on the shapes of distant galaxies to trace the hidden architecture of the universe. What makes this technique so revolutionary is that it gives us access to dark matter, not indirectly through rotation curves or velocity dispersions, but directly through its gravitational impact on light. Shear mapping has become one of the most vital tools for understanding the large-scale structure of the cosmos, the growth of cosmic web filaments, and the role of dark energy in cosmic expansion. Because the formation of cosmic structures depends on both the amount of matter and the way space expands over time, shear maps are sensitive to both. This makes them especially valuable for testing cosmological models. For example, if dark energy is causing the universe to accelerate, then structure should grow more slowly, leaving a distinct signature in the lensing pattern. By comparing observed shear maps to theoretical predictions, astronomers can constrain the properties of dark energy, test modifications to general relativity, and explore alternative gravity theories. It's not just about mapping what's out there, it's about testing the very rules that govern cosmic evolution. But extracting this information is no simple task. The distortions are minute, and galaxy shapes are naturally irregular to begin with. So it takes enormous datasets and sophisticated statistical methods to isolate the lensing signal. This is where modern sky surveys come into play. Projects like the Dark Energy Survey, the Kilo Degree Survey, and the upcoming Vera Rubin Observatory's Legacy Survey of Space and Time are designed to collect images of hundreds of millions of galaxies, with precise measurements of their shapes and redshifts. These datasets are then processed through intricate pipelines that correct for observational effects, like telescope optics, atmospheric blurring, and pixel noise, before performing the statistical averaging necessary to extract shear. The end result is a shear map, a two-dimensional projection of the mass distribution across the universe. But even that is just a beginning. By adding redshift information, astronomers can construct three-dimensional shear maps, or tomographic reconstructions, revealing not just where mass is now, but how it evolved over time. This time, evolution is critical, because it tells us how cosmic structures have grown over billions of years. In standard cosmology, small fluctuations in the early universe grew into galaxies and clusters under the influence of gravity. but this growth is sensitive to the amount of dark matter, the properties of dark energy, and the laws of gravity themselves. Shear mapping allows us to trace this growth directly, providing one of the few observational windows into how cosmic structures evolve. It's like watching a forest grow from saplings to towering trees, not by measuring each tree individually, but by analyzing the shadows they cast across the landscape. And just as the pattern of shadows can tell you about the size, density, and shape of the forest, the shear pattern reveals the underlying distribution and history of cosmic mass. Yet the potential of shear mapping extends beyond cosmology into the frontier of unknown physics. Alternative gravity theories, like F-gravity, scalar, tensor models, or brainworld scenarios, predict different behaviors in the growth of structure and the bending of light. By comparing shear maps with these predictions, we can test whether general relativity holds on the largest scales or whether new physics is required. This makes shear mapping one of the most powerful tools for probing the fundamental nature of gravity, a crucial step toward unifying it with quantum mechanics. Additionally, shear mapping can be used to detect massive neutrinos, which affect the growth of structure in subtle ways. The total mass of neutrinos, a key open question in particle physics, leaves fingerprints in the sheer power spectrum that next-generation surveys aim to uncover. In this way, the faint stretching of distant galaxies can speak volumes about particles that scarcely interact with matter at all. There's also a remarkable elegance to the idea that chaos can be tamed statistically. No single galaxy reveals the truth, but together, millions of imperfect, lopsided, distorted galaxies tell a clear story. Shear mapping is an art of collective clarity, where individual noise is averaged into cosmic signal. It's a reminder that in the face of overwhelming complexity, patterns emerge not from perfection, but from scale. And that's not just a lesson in astronomy. It's a lesson in how we learn anything meaningful from a noisy universe. When we can't see directly, we infer. When we can't measure in isolation, we aggregate. Through this lens, shear mapping becomes not only a scientific tool, but a philosophical metaphor. How truth emerges from distortion. How hidden forces shape what we see. How reality can be reconstructed from its shadows. Even aesthetically, the results of shear mapping are stunning. The mass maps produced by these techniques don't resemble traditional images of galaxies or clusters. They are abstract contour, rich portraits of invisible matter, like gravitational weather maps revealing high-pressure zones of dark mass. These maps have helped confirm the existence of massive dark matter halos around galaxy clusters, detect cosmic filaments stretching between galaxies, and even identify new gravitational lenses that might have gone unnoticed. As these maps improve in resolution and depth, they offer a new way of visualizing the universe. Not by its light, but by its pull, not by its glow, but by its gravity. And with upcoming missions like Euclid and the Nancy Grace Roman Space Telescope set to push shear measurements to new limits, the next decade promises a revolution in our understanding of the dark universe. So, the next time you look at an image of distant galaxies, remember that their shapes carry a message not written by stars, but by space itself. Each slight stretch, each faint skew, each imperceptible alignment is a clue, part of a grand mosaic that reveals where matter is, where it was, and how it got there. Shear mapping teaches us that reality is more than meets the eye, that even the smallest distortions, when read correctly, can expose the deepest truths. In the hands of those who know how to listen, the universe whispers not just in light, but in the bending of that light by the gravity of things we cannot see, and in that whisper lies the map. Not just to the cosmos as it is, but to the forces that made it so. The intergalactic medium, a hidden ocean between the stars. Not every void is empty. Some are filled with whispers, particles, and memory, so faint that even the most sensitive telescopes can barely trace them, yet so vast that they shape the very structure of the cosmos. Between galaxies, beyond the glowing arms of spirals and the fiery hearts of quasars, there lies an enormous, nearly invisible web of matter, known as the intergalactic medium, an expansive sea of ionized gas and ancient hydrogen that flows between the luminous islands we call galaxies. Unlike the dense clouds that form stars, or the bright disks that make up galactic spirals, the intergalactic medium emits almost no light, contains few stars, and yet holds most of the normal matter, baryons, in the universe. It is not a void but a medium, not silence but a quiet hum, threading through the darkness in long, wispy filaments and hot plasma sheets, serving as both the birthplace and the burial ground of cosmic matter. To understand the intergalactic medium is to understand what happens between everything else, to recognize that the space between galaxies is not a passive gap, but an active, evolving environment that determines how galaxies grow, how light travels, and how the universe came to be laced with structure at every scale. It is the unseen ocean on which galaxies drift, and its currents guide more than we ever imagined. The story of the intergalactic medium begins shortly after the Big Bang, when the universe was hot, dense, and uniform. As it expanded and cooled, protons and electrons combined to form neutral hydrogen in an era known as recombination, leaving behind the cosmic microwave background. For a time, the universe entered what we now call the Dark Ages, an epoch without stars, galaxies, or light, but filled with this neutral hydrogen gas. Eventually, the first stars and galaxies ignited, emitting ultraviolet photons that reionized the intergalactic medium, tearing electrons away from hydrogen atoms and returning much of the universe to a plasma state. This phase transition, cosmic reionization, was one of the most important events in cosmic history, transforming the IGM from a cold, neutral fog into a hot, ionized medium, and allowing light to travel freely across space. Today, most of the intergalactic medium remains in this ionized state, with temperatures ranging from thousands to millions of kelvins, depending on the region and the density of the surrounding cosmic structures. But despite its dominance in volume and its importance to cosmic evolution, the intergalactic medium is incredibly difficult to observe directly. It does not glow like stars, nor collapse into galaxies, but instead reveals itself through the way it absorbs and scatters light. One of the most powerful tools astronomers use to study it is the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars, caused by intervening clouds of hydrogen gas in the intergalactic medium. As the light from a quasar travels billions of light years to Earth, it passes through these diffuse gas clouds, each imprinting a tiny fingerprint on the spectrum. When analyzed collectively, these lines form a forest of absorption features that encode a map of the intergalactic medium's density, temperature, and motion over cosmic time. Through this technique, we've discovered that the intergalactic medium is not evenly spread, but forms a cosmic web of filaments and voids, tracing the underlying distribution of dark matter. Where the web is thickest, galaxies and clusters form. Where it's sparse, emptiness reigns. And between these extremes flows the medium, the intergalactic plasma that fills in the spaces and connects the dots. Within this cosmic web, the intergalactic medium exists in multiple phases. There's the cool photosionized gas that makes up much of the Lyman alpha forest, with temperatures around 10,000 Kelvin. Then there's the warm, hot intergalactic medium, WIM, with temperatures between 100,000 and 10 million Kelvin, likely formed by shock heating during structure formation. Finally, there's the hot X-ray emitting gas found in galaxy clusters, a denser and more extreme form of intergalactic matter. Each of these phases plays a different role in cosmic evolution. The cooler regions provide the raw material for galaxies to accrete. The warmer regions trace the dynamic, turbulent flows of matter as it streams into filaments and halos. In fact, the WIM is thought to host a large fraction of the universe's missing baryons, ordinary matter that appears to be absent from our local inventories, but is predicted by cosmological models. By detecting faint absorption in X-ray and ultraviolet spectra, astronomers are beginning to locate these hidden baryons, piece by piece, mapping out the intergalactic medium, not just as an abstract concept, but as a measurable structure. Beyond its role in holding matter, the intergalactic medium also acts as a filter and canvas for cosmic light. Photons traveling across the universe are absorbed, scattered, and redshifted by the intergalactic medium, changing how we see distant galaxies and quasars. Some regions of the intergalactic medium are so thick with gas that they can completely block the light from background sources, creating what are known as Lyman limit systems or damped Lyman alpha systems, which provide rich laboratories for studying chemical composition and gas dynamics. These regions often contain not only hydrogen, but heavier elements like carbon, oxygen, and silicon, traces of star formation and supernovae in early galaxies that enriched the intergalactic medium with metals. In this way, the intergalactic medium becomes a historical record, preserving the chemical fingerprints of countless generations of stars, even when those stars themselves have long since faded. It tells us not only where matter is, but where it has been and what it has become. Interactions between galaxies and the intergalactic medium are not one way, either. Galaxies feed on the intergalactic medium, pulling in gas through gravitational accretion and cold flows that sustain star formation. At the same time, they enrich and heat the intergalactic medium through feedback, stellar winds, radiation pressure, and galactic outflows that eject material back into intergalactic space. In extreme cases, powerful jets from supermassive black holes can drill holes in the surrounding medium, redistributing energy and metals across hundreds of thousands of light years. These feedback mechanisms are essential in regulating galaxy growth and maintaining the delicate balance of cosmic ecosystems. Too much feedback, and galaxies starve themselves of fuel. Too little, and they overproduce stars and collapse into overgrown bulges. The intergalactic medium, in this sense, is both nurturer and regulator, a cosmic circulatory system that connects galaxies into a broader environmental context. On even larger scales, the intergalactic medium defines the very skeleton of the universe. The distribution of its density fluctuations over time reveals how structures formed from the nearly uniform early universe to the richly textured cosmos we see today. By comparing observations of the intergalactic medium with simulations of cosmic structure formation, astronomers can test the validity of cosmological models and constrain key parameters like the matter density, the Hubble constant, and the nature of dark energy. And in the next generation of research, face centimeter line observations, emissions from neutral hydrogen, promise to revolutionize our view of the early intergalactic medium, revealing the epoch of reionization in real time and offering a direct probe of the first stars and galaxies. These observations, currently being developed by arrays like LOFAR and the upcoming Square Kilometre Array, will let us map the invisible universe in unprecedented detail, not just through light, but through the radio echoes of hydrogen itself. What makes the intergalactic medium so profound isn't just its scale or scientific value, it's the way it challenges our perception of nothingness. We often think of space as empty, a vacuum where only isolated islands of matter float, but the intergalactic medium reveals a different picture, one in which everything is connected by a faint, dynamic, evolving sea of matter. It's not a background, but a bridge, a living medium that binds galaxies into a coherent whole. It reminds us that most of the universe doesn't emit light, doesn't shine, doesn't scream for attention. Instead, it whispers, it sustains, it surrounds, and through careful listening, through spectroscopy, radio waves, and gravitational maps, we are slowly learning to hear it. So the next time you see a picture of a galaxy glowing beautifully in the darkness, remember that what you see is only half the truth. Beyond the stars, beyond the glow, beyond the visible, there is a vast and silent ocean, one that holds more matter than all the galaxies combined. one that remembers the first stars and still carries the breath of their fire, one that shapes the present and quietly prepares the future. The intergalactic medium is the space between. But it is also the story beneath, the unlit stage on which the universe performs, the fluid scaffold that makes the cosmos whole. In its stillness, it moves galaxies. In its darkness, it guides light, and in its silence, it speaks. Lagrangian points, invisible balancing zones in space. Out in space, everything is always moving. Planets spin, moons orbit, stars glide through galaxies. There's no stopping, no standing still. Not like on Earth, where you can sit quietly on a rock or rest in your bed. In space, everything falls and floats forever. But what if I told you that, even in all that endless motion, there are a few secret places where something can stay still? Places where a spacecraft, or even an asteroid, can just hang there. Not floating away, not falling down. Just perfectly balanced, like a feather resting in midair. These special spots are called Lagrangian points, and they're like invisible seats in space where gravity and motion cancel each other out, allowing objects to stay almost perfectly still. Now imagine two big things in space, like the Earth and the Sunday. Earth moves around the Sunday in a big loop, pulled by the Sunday's gravity while flying forward like a spinning marble on a string. But around these two massive bodies, there are 5 magical points where the pull of gravity, the push of motion, and the natural resistance to change all come into perfect harmony. That's where the Lagrangian points live. They're not made of anything, you can't touch them or see them, but they're real. Places made of balance, like the quiet center in a spinning whirlpool. Let's talk about them one by one. The first one, called L1, is right between the Earth and the Sunday. It's close enough to the Sunday that the Sunday's gravity is strong, but Earth's gravity still helps hold things there too. At L1, a satellite can stay in line between the two and always see the Sunday without being blocked. That's where a special observatory named SOHO lives. It watches the Sunday 24/7 and warns us about solar storms. Then there's L2, which sits just behind Earth, away from the Sunday. At L2, a telescope can float in Earth's shadow, shielded from bright sunlight. That makes it the perfect place for delicate instruments to see deep into space without being dazzled. That's exactly where the James Webb Space Telescope is, now gently gliding, steady and cool, while it looks farther than we've ever looked before. L3 is on the far side of the Sunday, exactly opposite Earth. We can't see it from here, and it's very tricky to reach, but it is still part of the pattern, like the hidden corner of a perfect 5-point star. Now, the last two are called L4 and L5, and they're even more special. These points form equilateral triangles with the Earth and the Sunday, like the corners of a perfect triangle in space. And unlike L1, L2, and L3, which are a bit wobbly and need little nudges to stay balanced, L4 and L5 are truly stable. That means objects placed there can stay put for a long, long time, even millions of years. Jupiter, the biggest planet in our solar system, has thousands of space rocks sitting in its L4 and L5 spots. We call them Trojan asteroids, and they've been riding along with Jupiter for ages, safely tucked into those quiet places. Earth might have its own little companions in these points too, small rocks or dust clouds, quietly drifting with us, hidden in the sunlight. Scientists are still looking for them. So why do these points matter? Because in space, stillness is rare. If you can find a spot where something doesn't have to use a lot of energy to stay in place, that's precious. Telescopes placed at Lagrangian points don't have to waste much fuel. They don't get too hot from the Sunday. They get a peaceful view of the universe, with less noise and more clarity. It's like finding a quiet hilltop above a noisy city, perfect for thinking, listening, and watching the stars. But some of these spots, like L-Fay and Lel-Fay, aren't perfectly still. They're delicately balanced, like trying to keep a pencil standing on its point. A tiny breeze could knock it over. That's why satellites there have little engines that give gentle pushes now and then, keeping them from drifting away. Even though they're not locked in place forever, they're still incredibly useful. The story of these points goes back over years, when a brilliant mathematician named Joseph Louis Lagrange wondered, are there places in space where the pull of two big objects would let a third small object just rest? And with careful thinking and beautiful math, he discovered the answer: yes, exactly 5 of them. And today, that math has become real life. We use those 5 points to send telescopes, satellites, and maybe one day even space stations. Think of Lagrangian points like invisible islands in a river. The river is always moving, always flowing, but in just the right places, a leaf could float there and never get swept away. Not because the river stops, but because the forces of motion balance each other out. And in a way, this isn't just a space idea, it's a life idea too. Sometimes we feel pulled in different directions, by work, by dreams, by worries. But what if, somewhere in all that motion, there's a special place for each of us where things feel balanced? A spot where everything pulls just enough, but not too much. A place where you don't have to fight the current. You can flow with it and still stay steady. That's what a Lagrangian point is. Not a pause from motion, but perfect motion in perfect harmony. So the next time you look up and imagine space as wild and chaotic, remember this: far above, millions of kilometers away, a telescope floats calmly, held in a perfect spot by the invisible hands of gravity. It doesn't drift away. It doesn't fall. It just stays exactly where it needs to be. Because even in a universe that never stops moving, balance is possible. You just have to know where to look. The cosmic axis, a strange alignment that shouldn't exist. Some discoveries don't challenge a theory. They challenge the idea that the universe is random at all. And in the vast quiet of deep space, buried within the delicate patterns of the oldest light we can observe, there appears to be one such mystery: a bizarre, large-scale alignment in the cosmic microwave background that points in a specific direction, as if the universe itself has an axis, a preferred orientation, despite every model insisting it shouldn't, known as the axis of evil. This term was coined not because of malevolence, but because of how deeply it violates the foundational principle of cosmology, isotropy. According to the cosmological principle, on large enough scales the universe should look the same in every direction. Uniform, directionless, statistically indifferent. Yet multiple independent observations have hinted that certain low-order multipoles in the CMB large-scale temperature fluctuations appear to align more than they should, all pointing roughly along the same axis across the sky. This alignment defies expectation, isn't predicted by inflationary models, and has stubbornly resisted dismissal as mere observational error. It's not just strange, it's statistically improbable, and if it holds under further scrutiny, it could mean the universe has a structure or symmetry baked into its very bones that no current theory can explain. The cosmic microwave background is often called the afterglow of the Big Bang, a uniform bath of microwave radiation emitted when the universe was just 380,000 years old. It serves as a snapshot of the infant cosmos, capturing tiny fluctuations in temperature that later seeded the growth of galaxies and clusters. These temperature variations can be decomposed into spherical harmonics, mathematical patterns similar to musical notes, which describe how fluctuations behave at different angular scales. Higher order modes represent small-scale structure, while lower order modes, called multipoles, capture the largest patterns in the sky. Specifically, the quadrupole and octupole components describe temperature differences across massive swaths of the sky, spanning tens of degrees. In an isotropic universe, the orientation of these multipoles should be random, but they're not. Instead, the quadrupole and octupole appear to be unusually aligned, both with each other and disturbingly with the ecliptic plane of the solar system. This correlation, first noticed in data from Mars and later confirmed in Planck satellite observations, suggests that the largest structures in the CMB, etched when the universe was unimaginably young, have a preferred direction, aligned with our tiny corner of the cosmos. This kind of alignment poses a problem not only for theory, but for assumption. If the universe is isotropic, why would the CMB's largest scale features point toward the solar system's plane? Is this a coincidence? A calibration error? An unknown foreground effect from the Milky Way? Scientists have worked meticulously to rule these out. Data cleaning methods, simulations, and cross-checks have been applied again and again. Yet the alignment persists, while the probability that such a configuration would arise randomly has been debated, estimated by some to be as low as 1 in 1,000. The consistency of its orientation has become harder to ignore. What makes it more perplexing is that the axis seems to correlate with other large-scale anomalies in the universe, including hemispherical power asymmetry and the cold spot, another mysterious feature in the CMB that may indicate a large underdense region of space. These aren't just isolated statistical blips. They might be symptoms of a deeper, hidden structure, a whisper of cosmology's blind spot. If the axis of evil is real, if it is not an artifact of instrument error or statistical fluke, then its implications are staggering. It could suggest a violation of isotropy, undermining one of the most cherished assumptions in cosmology. It might mean that inflation, the rapid exponential expansion of space post-Big Bang, wasn't as uniform as we thought. Some inflationary models propose that certain initial conditions could imprint directional dependence into the universe's expansion. But these models tend to be exotic and fine-tuned. Others invoke cosmic topology, suggesting that the universe may have a non-trivial global shape, like a torus or a dodecahedron, that wraps around in a way that forces alignment. Still others speculate about new physics entirely: primordial vector fields, anisotropic curvature, or pre-Big Bang remnants that somehow survived the inflationary smoothing. In all these scenarios, the early universe wasn't truly directionless. It had a preferred orientation, and that orientation is still visible, painted faintly onto the sky, like a scar from a forgotten event. Of course, not all physicists are convinced. Some argue that focusing too much on the axis risks apophenia, the human tendency to see patterns where none exist. After all, the CMB is a single sky, a one-off realization of the universe. Statistical anomalies are bound to happen somewhere in such a rich dataset, especially when multiple comparisons and a posteriori reasoning are involved. Yet, unlike fleeting noise or localized glitches, the axis of evil is global, persistent, and stubbornly coherent across datasets and cleaning methods. It is not a trivial coincidence. It cuts to the very heart of whether the universe we inhabit is truly random at its largest scales, or whether some ancient symmetry, long erased from every other observable, still lingers in the background. What makes this even more intriguing is how the axis lines up with our solar system's motion. The ecliptic plane, the dipole anisotropy caused by our movement through the CMB, and the orientation of certain cosmic structures all seem eerily correlated. Is this a strange cosmic joke, or does it hint that our observational vantage point somehow matters more than we assume? Some theories suggest we may live in a special region of the universe, an idea once heretical, now cautiously entertained in the form of cosmic variance. Others point out that this could be evidence of observer bias, a subtle foreground contamination, or even a breakdown of the Copernican principle, the belief that we do not occupy a privileged position in the cosmos. If the axis is real, and if it aligns with our local structures, then either the universe is aligned with us, or we misunderstand how deeply our observations are entangled with our location in space-time. In the end, the axis of evil remains one of the most tantalizing puzzles in modern cosmology. It doesn't break any laws outright, but it bends the expectations so far that we're forced to squint. It's not a discovery of a new particle or a gravitational wave. It's a hint that our grandest assumptions might be wrong. And in science, that is often more valuable than a clean result. The axis dares us to look harder, to question deeper, to rebuild our models with fewer comforts and more possibilities. It reminds us that even in an era of high-precision cosmology, where satellites map the universe in exquisite detail and simulations run across supercomputers the size of cities, Nature still holds surprises that no model predicts. It's the universe whispering again that it is not fully known, and maybe never will be. So the next time someone tells you the cosmos has no center, no edge, no preferred direction, remember that the oldest light we've ever seen, the light from the surface of last scattering, born when the universe was barely out of its cradle, has something to say about that. It leans, ever so slightly, in one direction. It aligns. And whether this is a statistical ghost, an observational artifact, or a genuine imprint of the cosmos' earliest structure, it challenges us to ask a dangerous, beautiful question. What if the universe isn't as impartial as we thought?